Okay, I will make it. Yeah, now I will make it. I will make it full screen mode little later.
Okay.
But at least,
Okay,
but
okay.
at least, yeah, I can make it. I can make it. I will. So this is. This is the
Now
full
I
screen. This is the
can.
full screen mode. Can you see?
Yes, yes, sir. Perfectly.
Okay. 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 So we can start. So we can start. I'm ready. I'm ready. So we can start.
Okay.
We can start after a little while. After a little while.
Yes, sir. We can start, I think, by 10 a.m., sir. We have scheduled like that.
Yes.
By 10 a.m.
Yes.
Okay.
Yes. Yes.
Okay.
Okay. Okay. We'll start.
Okay.
At 10 We'll start at 10 a.m. Okay.
Okay.
Okay. Fine.
Okay, thank you, sir.
Okay. Good. It is set up.
Okay. Let it be there, sir.
It is set up properly.
Okay.
Yeah, I will be there. I will be there. I just want to check one video if it is working or not.
Okay, okay, okay.
It should work. It should work. So this video is working, right?
Yes, sir. Yes, sir. We can see that.
Okay, good. Perfect. Perfect. No.
Okay. No issues.
I will leave it. I will leave it on the first slide, and then we
Okay.
can.
We can resume at 10 a.m., sir.
Good morning, Deepa. I am ready to start whenever you are.
We can start shortly, sir.
Okay, no problem.
Good morning all. Hearty welcome to day 3 of AICT sponsored 6 days virtual STTP on robotics, artificial intelligence and control. Today, for the first session, we have Dr. Ashitava Ghoshal with us, who would be dealing with the topic overview of recent research in robotics at IISc Robotics Lab. Professor Ashitava Ghoshal is working in the Department of Mechanical Engineering at the Indian Institute of Science, Bangalore since 2015. He did his post-graduation at the University of Florida after completing his bachelor's degree program at IIT Kanpur. Professor Ghoshal received his doctoral degree from the prestigious Stanford University, USA in the year 1986. He is an expert in the areas of kinematics, dynamics, control and design of robots, and other computer-controlled mechanical systems, theoretical and numerical investigations of nonlinear dynamical systems, kinematics of barrel mechanisms and manipulators, and design of mechanical systems, biomedical devices, and CAD/CAM. Apart from being the author of 3 books, Professor Ghoshal has also published in 64 journals and 37 conferences. He holds the co-ownership of patents on a portable system for refrigeration, an apparatus to maintain temperature of an object, safety cap and sealing system for LPG cylinder, laparoscopic apparatus, foldable bicycle, and device for transferring subject from source platform to target platform. We welcome you, sir.
Okay, thank you very much. So, thank you very much for inviting me. So, today I will show you some of the activities of the robotics and research lab at IISc. So, shall I go ahead and start? Everybody can hear me?
Yes,
Hello?
sir.
Yes, sir.
Okay, so I will start. So today I will show you some of the work, research activities in the robotics and design lab in IISc. So my name is Ashitava. Thank you for kind words introducing me, Deepa. So let's proceed. So most of the work which I has been done by my students. So there is Mithun Menon, who has worked on hyper-redundant robots. I will show you some work which he has done. There is also VC Ravi. He has done work on hyper-redundant robots also. Then we have Puneet Singh. He worked on how to resolve redundancy in human arms. He has worked on parallel robots for tracking of the sun. Mohit Acharya also on the same topic. Then we have Ashwin. He has worked on actuated endoscopic end effector. And recently, a new student called Soumya Kanti Mahapatra, he is working on cable-driven robots. So there are many other students, but these are some of the directly involved with the projects. The funding of this was done by Robert Bosch Center for Cyber Physical System. So I'm going to discuss the content in this talk. very briefly do some introduction. Then I am going to show you 3 new areas of activity in our lab. So as I said, you must have hinted that the first one is serial hyper-redundant robots and human arm. Then we have redundant parallel robots for sun tracking. And finally, we have actuated flexible endoscopic end effectors. So very quickly, we'll see throughout this talk, there is this whole idea of a redundant or a hyper-redundant robot. So very quickly, what is hyper-redundancy or redundancy in robots? So a rigid body in 3D space has 6 degrees of freedom. Okay, everybody knows this. So you can position using 3 coordinates, let's say x, y, z, and you can orient a rigid body in 3D space using another 3 parameters, maybe 3 rotations like roll, pitch, yaw. If you have 2 rigid bodies in 3D space connected by a joint, so then the degree of freedom of that combination is 2 into 6 because there are 2 rigid bodies minus the number of constraints imposed by a joint. Okay, so for example, if you have 2 rigid bodies connected by a hinge joint, so the second rigid body can only rotate relative to the first rigid body. So the hinge joint is imposing 5 constraints. There is a very famous formula called the Grubler's-Kurzbach formula or the Grubler's criteria, which tells you that the degree of freedom of a multi-body system, several rigid bodies connected by joints, is given by lambda into n minus j minus 1 plus the degrees of freedom at each joint. So there are j joints and we find the degrees of freedom at each joint, which is fi, and then sum it over. And this quantity lambda basically tells you whether you are moving in 3D space or you are in plane. So if you are in 3D space, then you have to use lambda equals 6. If you are in plane, you have to use lambda equals 3. Okay. So if you look at this figure on the right, this is a planar 3 degree of freedom robot. It consists of 3 rotary joints, 1, 2, 3 rotary joints. There are 4 links. So in this, N also includes the fixed link. So I have 1 fixed link, 2nd, 3rd, and 4th. So if you substitute 3 into 4 minus 3 minus 1, so then that will be 0. And then the degrees of freedom at each joint, these are rotary joints, are 3, 1 plus 1 plus 1. So hence you will get 3 degrees of freedom. So what it means is that this multi-body system or this planar robot can position and orient an object which it is grasping in this schematic grasper arbitrarily in a plane. Okay, so I can put it at any point xy and I can also rotate at that xy this object which I'm grasping. Okay, so this is the typical non-redundant case, and we can derive the equations, kinematical equations for this object. So if I say that the position of this object is xy and the orientation is phi, so in a plane a rigid body has 3 degrees of freedom, so x, y, and phi. And obtain this x, y, and phi in terms of the rotations at the 3 joints. So I have theta 1, theta 2, theta 3, which are the 3 rotations. And you can derive by simple geometry and trigonometry that x is some L1 into cos theta 1 plus L2 into cos theta 1 plus theta 2 and L3 into cos theta 1 plus theta 2 plus theta 3. You can see the x coordinate of this point will be projection of this vector, which is L1 cos theta 1. Then projection of this, the absolute angle with the horizontal is theta 1 plus theta 2. So hence you will get L2 into cos theta 1 plus theta 2. And then finally L3 into cos theta 1 plus 2 plus 3. The y coordinate will contain sine, that is obvious. And finally, the orientation of this last link will be theta 1 plus theta 2 plus theta 3 because the orientation is with respect to the reference coordinate system. Okay, so if you look at these 3 equations, if I give you x, y, and phi, I can at least conceptually solve for theta 1, theta 2, and theta 3. Okay, because I have 3 unknowns and 3 equations, if I can solve. And in fact, this is the inverse kinematics problem of this robot. And there are many books in which this problem is solved. So this is the typical non-redundant case. Okay, so I have 3 equations in 3 unknowns, and I can obtain theta 1, theta 2, theta 3 for a given x, y, and phi. Now let's consider the case when I really don't care what is the orientation of the last link. So basically I have only these 2 equations, x and y, which are related to theta 1 plus 2, and theta 1 plus 2 plus 3. Okay, so hence I have only 2 equations. Okay, so I have 2 equations in 3 unknowns. So if I give you x and y, then I cannot find theta 1, theta 2, and theta 3 uniquely. There will be infinite ways of reaching that point. Okay, this is basic algebra, that I have 2 equations in 3 unknowns. If I give you the left hand side, I cannot find all the solutions in the right hand side uniquely. So this is called the redundant case. So given the position and orientation of the end effector of a robot, if the number of joints is more than 3, so more than 2 or 3 in the plane, and more than 6 in 3D space, there are infinitely many possible solutions. Okay, so what do we do? People build robots with many more joints. So basically what we need to do is we need to invent or impose an additional constraint to solve for the theta 1, theta 2, and theta 3. Okay, so that is the basic idea. And this imposing an additional constraint is termed as resolution of redundancy. So what can we do? So the simplest thing that one can think of is we do optimization. Okay, so in any optimization problem, we can have an objective function, and then we have some constraints, and then we can numerically optimize that objective function such that we get a unique value. Okay, everybody has seen optimization, I am assuming. What is optimization? So in this case, one obvious objective function is to say that we are going to minimize theta 1 squared plus theta 2 squared plus theta 3 squared. Okay, what is this objective function? It is telling you that I am going to minimize the motion of the joints. So I want to go to xy. Okay, I have infinitely many values of theta 1, theta 2, and theta 3, but I want to pick a theta 1, theta 2, theta 3, which minimizes this objective function. And of course, we have these 2 constraints. So we have x given by L1 C1 plus L2 C12 plus L3 C123, and y given by L1 S1 plus L2 S12 plus L3 S123. Okay, so everybody following? Because I can't see any hands. If there are any questions, you have to tell me. Okay, is that okay?
Yes, sir.
Okay, so I can't see any hands otherwise, or any way to know if everybody is following or not. Okay, so we can optimize, or we can solve this optimization problem using MATLAB or any other software, and we can find theta 1, theta 2, theta 3 given x and y, because we are given x and y. So in this example, what I'm saying is I'm going to track a trajectory in the workspace of this robot. The workspace of this robot is one big circle and one small circle. Okay, so this outside circle is L1 plus L2 plus L3, and this small one is L1 minus L2 minus L3. So I want to move along the y-axis, this dotted line. Okay, this is a chosen trajectory. We can choose any other trajectory. We can choose any other series of xy points, and I want to solve for theta 1, theta 2, and theta 3. So I solve this optimization problem, and you can see that theta 1 minimum is given by this line. Okay, so one of them is a small circle one of them is a big circle, and one of them is a hollow circle. Okay, so this plus is theta 3. Okay, this one is theta 2, and this one is theta 1, the big one. Sorry, the big one is, I think, theta 2, and the small one is this one. So as I move along this trajectory, I can solve for theta 1, theta 2, and theta 3. I can also plot what is the objective function. So summation of the squares of theta 1 plus theta 2 plus theta 3. So this is really dark line is the objective function. So this solves the problem, okay? Because if somebody has designed a redundant robot, let's say in this case, 3 degree of freedom robot, but I want to use that robot to track this trajectory along the y-axis, okay? I cannot solve unique values. Inverse kinematics is not possible, but I can use this optimization to move along this trajectory, and I need to give. So if I have a controller, I calculate all this theta 1, theta 2, and theta 3, and I pass on to the motors these values of theta 1, theta 2, and theta 3, and then this end will move along this direction, okay, along the y-axis. So this is a resolution of redundancy, and what we are doing is we are minimizing the joint rotations. Okay, so this is a very well-known standard way of finding a unique solution if you have a redundant system. You minimize something. We can also do one more nice thing, which is called redundancy and isotropy. Okay, so let me just very briefly explain what I want to do here. Okay, so I have this planar 2 degree of freedom robot. I have x is given by L1 cos theta 1, L2 cos theta 1 plus theta 2, y is L1 sin theta 1, L2 sin theta 1 plus theta 2. This is very, very standard, obvious, and it can be obtained by simple geometry. So I can find what is the velocity at that point at some theta 1 and theta 2. So I can compute the derivative, which is x dot and y dot. So it will be a function of theta 1 dot and theta 2 dot. And you can take the derivative and reorganize in a matrix equation. It looks like x dot left hand side is some minus L1 sin theta 1 minus L2 sin theta 1 plus theta 2 minus L2 sin theta 1 plus theta 2, which you can see. Where did this minus come from? When you take the derivative of cos, you will get minus. Okay, and then you reorganize it, and then you say this first row is multiplied by theta 1 dot, this is multiplied by theta 2 dot, that will give you x dot. Likewise, y dot. So this matrix is called the manipulated Jacobian matrix. It's a very well-known standard matrix in robotics. Every time there is a joint and there is a Cartesian velocity and a joint velocity, they are related using this Jacobian matrix. So from this Jacobian matrix, I find another matrix which is J transpose J. So J is this matrix. And then I find the eigenvalues of this matrix. Okay, everybody knows what is an eigenvalue problem. You find G into theta dot minus lambda into theta dot is equal to 0. And the eigenvalue problem is determinant of G minus lambda I is equal to 0. And then you solve for lambda 1 and lambda 2. In this case, there are 2 eigenvalues because this matrix is 2 by 2. Okay. And it turns out that the 2 eigenvalues are this G11 plus G22 and so on. G11 plus G22 whole square minus 4. So it's a quadratic equation. So I can find the roots of the quadratic equation. So it is minus b plus minus square root of b square minus 4ac divided by 2a, standard formula. And we can find that the maximum velocity at this point is given by square root of lambda 1, and the minimum velocity is given by square root of lambda 2, where lambda 1 and lambda 2 are the 2 eigenvalues. And if I plot the tip of the velocity vector for any θ1 dot and θ2 dot. It will lie on an ellipse. Okay, so what is it telling you? For this robot, at any point, if I change θ1 dot and θ2 dot, the tip of the velocity vector will lie on an ellipse. The maximum value, which is the major axis of the ellipse, is square root of λ1. The minor axis is square root of λ2. Okay, so another way of saying that there are certain directions at that point where I will get more velocity, and some directions I will get less velocity. Or another way of saying that in some directions, for the same effort, I will get more output than in other directions. So you must have heard of mechanical advantage, okay, in lever and pulley and various other places. Okay, so this is an extension of the idea of mechanical advantage for a robot. Okay, so the bottom line is, at any random point, any generic point, I will have this ellipse. Now let us consider a 3 degree of freedom robot. So I have 2 link, but I have also one more link. Okay, so the velocity vector at that point can be written in terms of θ1 dot, θ2 dot, and θ3 dot. Okay, so basically what we have is some psi1 into θ1 dot, psi2 into θ3 dot, and so on. So since we have one redundant joint, I can choose one of these angles, θ1 dot or θ2 dot, as some psi3 into θ3 dot is alpha1 psi1 θ1 dot plus alpha2 psi2 θ2 dot. Okay, so this alpha2 is not correct. This should not be there. This is a typo. Okay, so I can choose one of the joints as a function of the other 2 joints, as a linear combination of the other 2 joints. And then I can substitute back psi3 θ3 dot into this equation. Then I will have a velocity vector in terms of psi1 θ1 dot, psi2 θ2 dot, alpha1 and alpha2. Now I can compute θ3 dot, or I can choose θ3 dot such that the eigenvalues of the resultant G Jacobian matrix are same. Okay, can we do that? Yes, because if I substitute psi3 into θ3 dot back into this, so I will have V as a function of θ1 dot and θ2 dot, exactly same as this. So this one will become this is the old psi1 and this is the old psi2. But now after doing all these things, we will have some 1 plus alpha 2 and 1 plus alpha 3, and some alpha 1, 2, and 3 will also show up. Alpha. Okay. So I can choose θ3 dot such that the eigenvalues are equal. Okay. So if I choose θ3 dot and if the eigenvalues are equal, then at that point the velocity vector, the tip of the velocity vector lies on a circle. Okay, because the eigenvalues are equal. So what have we done? We have used θ3 dot, which is the extra variable, which is the redundant variable, to make this velocity distribution circular, which means all directions, the effort and the output are same. So if I give some effort, the output in all directions are same. So this is called isotropic. Okay, so if anyone who has done some course in solid mechanics, we assume that a material is isotropic. Okay, what does it mean? That the properties are same in all directions. In this case, isotropy means that the tip of the velocity vector is equal magnitude in all directions at that point. Okay, so this is very useful because what is happening is, whatever I do at θ1, θ2, and suitably chosen θ3, okay, I am getting uniform mechanical advantage or uniform output in all directions. So this idea can be extended to 3D motion. In that case, from ellipse, you will get to ellipsoid, and you can also extend to angular velocity vector. Okay, so this is one way of using an additional joint theta 3 dot to make the velocity vector uniform in all directions. Okay. So let's continue. So let's look at a human arm. Okay, so a human arm till the wrist, okay, without counting the degrees of freedom at the fingers. We will not worry about the fingers. There are many degrees of freedom at the fingers. Okay, every finger has some like 4 joints. There are 5 fingers. So that itself is 20 joints in the fingers. But if you ignore all the fingers, so till the palm, I have 3 degrees of freedom at the shoulder. Then there are 2 degrees of freedom at the elbow, and there are 2 degrees of freedom at the wrist. So I have 7 degrees of freedom, and I need only 6 degrees of freedom. Okay, so as I remember, in a robot moving in 3D space, I need 6 degrees of freedom to position and orient an object in 3D space. So question is, in human arms, there is a 1 extra joint, and it is a redundant system. Okay, so how do we use the redundancy? So this is a question which one of the students investigated. So what we have is an experimental setup where this person is sitting, his head is somehow fixed. Okay, he holds a manipulator, a 2 degree of freedom planar manipulator, which he can move around. Okay, and there are sensors on the manipulator, and then there are sensors mounted on the human arm, okay, electromagnetic trackers, which can measure these angles, which can measure this theta, clavicle, shoulder, elbow, wrist, and so on. Okay, and we can obtain this XY point both from the manipulator and also using kinematics. We can find theta 1, theta 2, theta 3, and theta 4, these 4 angles, and find X and Y. And we, for different subjects, these link lengths L1, L2, and L3 and L4, they are different. Okay, however, so somebody can be tall, somebody's arms are longer, and so on. So for each of these subjects, I know X and Y from the robot, and I can also obtain X and Y using kinematics, and I make sure that this L1 through L4 are obtained to match the 2XY. Okay, so that is one part. Second part is, while you are moving this arm, okay, end of the robot, you cannot see your whole arm. Okay, what you see is a projection of a tracker. There is a projection system. There is a some kind of a TV screen, and there is a mirror here. You see what is happening here on a screen here as a dot. Okay, and this dot is moving. As you move the arm, that dot will move. Okay, so now that we have all this experimental setup, and we have a person, so there are many persons who were chosen to do these experiments. So what is the experiment? The experiment is the following. So on that screen, on that mirror, you see one white or one cursor here, and you see a target. And you are asked to move your hand such that you go to this target in some reasonable time, in a few seconds. We cannot take forever. Okay. And while you are moving, we want to record the motion at the 4 thetas. And I also measure what is happening to the X and Y. So as you can see, so the person starts from here and wants to go here. You will never go exactly straight. So there will be some small deviation. Okay. So that is what happens when you have a subject which is trying to perform a task. And then these targets appear at random in 8 directions. So it could be 0, 45, 90, 135, and so on. So once this will appear, you have to move here and come back. Then suddenly this will appear, you have to move from here to there and come back. So this is the task. And at each time we are recording the motion of the hand, recording the motion of all the joint angles. So after some 80, 90 turns, trials, so basically on the average 10 along each directions, there are 8 directions. So after about 80 trials, okay, we the robot which the person is holding starts applying a force which is perpendicular to the direction of the motion. Okay, and this force is also proportional to the velocity. So initially the velocity is small, the force applied is very small. Somewhere in the middle of the path, the velocity is highest and the force is also highest. And as you reach the target, the velocity is small and the force is also small. Okay, so what do you think will happen to the motion of the hand when you start applying a force? Any guess? Everybody is awake? At least some guess should be there, no? So look, in the previous case, as I moved, it is more or less straight. Go ahead, tell me. So what do you think will this picture will look like here, where my cursor is? Any ideas? Okay, I will show you. Okay. So what you will see is, because of the force initially, which is this red trials, this is the first 5 trials after the force is switched on. There will be a large error. So this red lines are the initial trials, first 5 trials as soon as the force is switched on. And then you keep on doing this task. After some time, you start learning. Okay, then your trajectories become more straight. It is not fully straight, but it becomes straight. Okay, so basically this is showing that you learn that there is a force which is being applied to your hand. Okay, and then you compensate for it. So you do this for a while, and then we switch off the force. Okay, so once you switch off the force, what will happen is you still think that there is a force which is acting initially, okay, and you overcompensate. So as soon as the force is switched on, you go in this direction, which is along the direction of the force. When this force is switched off, you overcompensate and you go in the opposite direction. This makes sense? Anybody thinks that this doesn't make sense? Is it clear to everybody, this experimental result?
Yes, sir.
Yes, sir.
Okay, so it sort of makes sense, except now we have actual data. So what this, all these nice different colored curves are actually numbers, okay, because we have recorded θ1, θ2, θ3 and θ4 by these trackers. We have also recorded X and Y of the robot. So we have actual numbers. So if somebody says, how much is the error? I can actually go and measure. Okay, how much is the error when there is no force? When it is normal, I can tell you that this is the maximum error while going from origin to 45-degree direction or origin to 135-degree direction and so on. So I can actually plot all these errors, okay? And in fact, that's what we do. We will plot the maximum error, okay, along a trajectory at different directions. So for example, these oranges are 225 degrees and so on. And then we plot all these maximum errors. So as you can see, the maximum error, which is happening at the maximum velocity, is like all of the order of something like 7 centimeters, okay, for this person who is doing these trials. But what you can see is as he learns, these errors keeps on going down. And it is possible to fit a curve, which is an exponential curve. Exponential because people have studied learning and they think learning is always exponential. Okay, so whatever you have learned, next time you learn faster, always. Because you base your new learning is based on the older learning. So it is an exponential curve which we can fit. And the exponential curves looks like this, these solid dark lines. Here there is not much of an exponent. It is very, very close to horizontal because the error is small. Okay, here initially the error is large and later on the error is smaller. When you switch it off, the force, the error suddenly becomes larger, but in the opposite direction, and that also goes to 0. Okay. So if you look at, this is for one subject, one person, and I can do that for 10 subjects. In fact, this is experiments were done for 10 people. Okay, each subject, this experiment takes about 2 hours. So, person will sit and do all these trials. So for 10 subjects, again, you can find that the maximum error looks like this. So the shaded region around this dark red line is the variation for subjects. Okay, different subjects will have different errors. Okay, so this is the solid line, which is the average of all these subjects, exponent, and the shaded region around us, small thin lines, I hope you can see, are for the variation of each subject. So in all, even for 10 subjects, what you can see is the error is very small initially, then it is sort of dying down. Of course, there are oscillations, and in the opposite direction also it is looking like this, this fitted curve. Subjects, later on we have done for many more subjects, this trend is seen, that when there is no force, the error is small. Suddenly when you apply a force, the error becomes very large, which dies down, the error becomes smaller. And when you switch off the force, the direction of the error changes, but then it also dies down as you start learning. Okay, so now let's see how we can analyze all this data that we have. So we have a model, which is that X and Y, the tip of this hand, is related to those 4 angles, 4 rotations, clavicle, elbow, joint, all those things, wrist. So those are denoted by theta 1, theta 2, theta 3, and theta 4. And as I said, we have found L1, L2, L3, and L4, those link lengths, such that those two XY match. Okay, so we have a model which tells you that the position of this tip of this hand is given in terms of these 4 angles. So the joint space is 4-dimensional. Okay, so it's an element of R4. The task space XY is 2-dimensional. Okay, so if you take any value of theta 1 through theta 4, it maps to another point in the task space. So given theta 1 through theta 4, I can compute X and Y. But there is one subset of this task space, which is called the null space of the Jacobian matrix, where I can be at the same XY, but the interior angles, some of the angles, there can be variation. Okay, so you can do this experiment yourself. So I can reach the nose by the finger, but then my elbow rotation and shoulder rotation can be different, although my tip is at the same place. Okay, my finger is at the same place. So that is what is shown here, that the tip is at the same place of this finger. However, there are many possible values of these joint angles. However, if you look at some other point outside the null space, okay, then this point will map uniquely. Okay, so all the points outside this null space, if I move these joints, the tip will also move. So this joint space has 2 parts, one which is the normal and one which is null space. Null space means that there are internal motions of the joints of your hand, okay, which does not change the X and Y, the tip location. Okay, so and I want to get an idea about how large this null space is. Okay, so how do we do? It is done in robotics, that we compute the Jacobian matrix. The Jacobian matrix is derivative of x with respect to theta 1, y with respect to theta 1. That is the first column. Second column is with respect to theta 2, and so on. We compute the Jacobian matrix for the average theta. So while you are going at the peak velocity, so there is an average and then there is a variation of theta. So we find for the average theta, and then we find the variation from the average for every theta which you measure. So this is the average. So minus the instantaneous theta for a subject is delta theta. And what we will do is we will find the null space of this Jacobian matrix, which we can find. It's two-dimensional, because this is a four-dimensional here and two-dimensional here. So the null space will be two-dimensional. You find the null space, and let's assume that the null space vectors are psi1 and psi2. You project this theta variation onto the null space, and then you sum it over. And then you find the square of this quantity theta square divided by the number of trials. Okay, so every person is doing many trials. So we need to find a single number which tells how big is the null space for that person. Okay. For every person, this joint space is four-dimensional, the task space is two-dimensional. We know that there is some part of this joint space which does not affect the tip motion. And I want to get an estimate of how big is this space, and that is the way to do it. Okay, so we find the variation about the mean, then we project the variation onto the null space along these two directions, sum it over, square, and then square that theta r, okay, which is the redundant degrees of freedom, square divided by n, the number of trials. Okay, is that clear? It's not very hard. Okay, so now we have a number which is called Nj, which was here. So this is a number which is Nj, which we have computed based on all this data for all the persons. We also have the learning rate, that beta for each person. And we plot beta and null space for every person. And we did these experiments with the person, and the person was asked to use his dominant hand, which is sometimes the right and sometimes the left hand, and sometimes the non-dominant hand, which is the other hand. Okay, so these dots tell you that this person has a null space of 0.06, let's say, and the learning rate is maybe 1.5 into 10 minus 3. One more person has a null space of 0.2 and a learning rate of 5.75 into 10 minus 3. Okay. So we can plot both Nj and beta for each one of these persons and see that it falls on a best fit line. Okay. So we are going to this. Blue dots are random, which are for the non-dominant hand. Red dots are for the dominant hand, and we fit a line through these points. So what does this? And this line is reasonably good line because there is something called R value and there is something called P value when you fit a line. So R value is this R square value of any fits, and P value is the probability that this fit is not by chance. So this P value should be less than 0.05. Otherwise, could be just a random chance. So what you can see is this R value is 0.72. Okay, P value is 0.18. So which means it's okay. It's a good fit. It will give you some result. So what it tells you that there is a strong correlation between Nj and beta. In English, people who have large null spaces, who have larger Nj, they also learn faster. Okay. So we also obtained what is the variability in the task space at the end of the motion and also learning rate. And here you can see that there is no correlation. Okay. So the R value is very poor and the P value is very large. So what does this tell you? It tells you that we know the human hand is redundant. Okay, it has 7 degrees of freedom. In this model, the redundancy is 2 degrees of freedom. Okay, because there are 4 joints and X and Y. We have computed a null space for each one of these 10 people who did these experiments. And we found that those who are using null space or those who are using the redundancy when the force is being applied, okay, they learn much better when the force is being applied. Okay, so their learning rate is higher. So is that interesting thing or not? What do you think? So any sportsmen are there in that group? Somebody who plays tennis or somebody who is playing cricket? Are there any sportsmen in the group or not? Am I audible?
Yes, sir. You are audible, sir.
But I want to know if there are any sportsmen in the group or not.
I think we have no one in this group, sir.
No one who plays any sport, tennis, cricket, badminton.
Dear participants, kindly reply.
Okay, don't worry. Okay, so if you are playing sports, how do you learn how to hit better and better? Okay, you do the same trials over and over again, right? That is the standard way to learn something better. However, this experiment is telling you that you have to learn to move in different ways. You have to use the variability that you have in your hand. Okay, so that is why it's an interesting result. Okay, and this is published in some very well-known journal called Proceedings of the National Academy of Sciences in USA. Okay, it's very, very hard to publish there. Okay, so let's continue. So human arm, the redundancy or use of redundancy helps in learning. Let's continue. As I showed you that we have this errors in all the 8 different directions. So we can plot the error. Okay, so this figure shows a plot of the error in the 8 different directions. So when there was no force, the errors were very small. Initially, as soon as the disturbance or the force was switched on, the errors are very, very large. And then towards the end, the errors are becoming again small. Okay, so I can plot the eccentricity of this ellipse. The eccentricity is measured by minor axis. So eccentricity initially is very large, and then the eccentricity is slowly decreasing. So this is the mean across all the 10 subjects, and this variation is there, which is the shaded region. So the largest error across all subjects, across the 10 subjects, was found to be around approximately 100 degrees. So if this is 0, the horizontal is 0, the error largest is in not vertical upwards 90, but little after that. The other important finding is that the error ellipse is large when the force field is applied, and it decreases with trials. And third important result is the error ellipse becomes less eccentric. It is becoming more circular. However, remember I had shown you that for a 3 degree of freedom robot, I can make it circular. So in the human arm, it is decreasing in eccentricity. It is tending towards a circle, but never a perfect circle. A perfect circle would have been 1 when the major and minor axes are equal. Okay, but that never happens. Okay, so there is a difference between mechanical systems and human hand. Okay, let's continue. Now we look at redundancy in hyper-redundant robots. Okay, so as I said, we need to impose additional objective functions to resolve the redundancy. So there are various ways of doing it. One is using the pseudo inverse of a Jacobian matrix. So Jacobian matrix is non-square. So there is something called the pseudo inverse, which we can use. We can also use these backbone curves, and we can also optimize joint torques. So what I'm going to show you is another method which some students have developed here. This is using a tractrix curve. Okay, so this is well known. This is invented by Leibniz, who was a very famous mathematician. He invented calculus, actually. So what he studied was, suppose there is a link, a rigid link, which is lying along the y-axis. So the head is at 0 and the tail is at 10 units long. And I'm going to move this head, which is this red dot, in a direction parallel to the x-axis. So I move from S to P, then P to P prime, and P prime to T, and so on. And the tail of this link is moving such that the velocity of the tail is along the link. Okay, that is the constraint. That is the extra constraint which you are imposing to make sure there is a unique solution for the motion of this tail. If you don't put anything, then if you move this, the tail can move parallel to the head, no? Or if you move this, the tail can go in some arc of a circle into some other direction. Okay, but we are going to ensure that the velocity of this point, the tail, is always along the link itself. Okay, in such a constraint, there is a curve which is traced by this tail at this point, and this is called the tractrix. Okay, and if you move dp from p to p prime dp, this tail will move from O to O prime, and this distance is dr. Okay, so we can derive the analytical expression for this curve, and I will show you that it is known that this dr will be less than dp always, or equal to. Okay, so we have an analytical expression of the curve, and then I want to use this idea to a redundant system. So basically, what do I have? I have this long chain of robot with many joints. I move the head by some distance. I calculate the motion of the tail using the tractrix equation. Then for the previous link, the motion of the tail of this link will become the motion of the head of the previous link. And again, I calculate the motion of the tail of the previous link, and so on, all the way to the end. Okay, so move Jn towards desired direction, compute motion of Jn minus 1 using tractrix equation, compute Jn minus 2, and all the way to J0. And as I said, dr is always less than or equal to dp. Okay, I haven't proved it, but it is true. Okay, you can show that this dr, the motion of the tail, is always less than or equal to dp. Okay, so this algorithm basically minimizes the linear velocity of the tail. Okay, so as a result, since all the motions are smaller and smaller and smaller, it looks like that the motion is getting washed out as we traverse down the chain, and this we can prove mathematically. Next, built a hardware which consists of 8 links. So these are serial robots. There are motors here, servo motors, which can make this link rotate with respect to the previous link by plus minus 90 degrees. There is a controller board which was developed, and we sent signals to this controller board using this RS-232 serial interface. So basically, we will, for a given motion of the head, okay, we will compute how much each joint should rotate and send the commands through this cable. Okay. And we are going to move this very slowly because it is not for high speed motion, these robots. Okay, it's a low speed operation. There is no dynamic compensation. It can slip. Okay, and we also make sure that the trajectory of the head is such that these two links or some two links do not hit each other. Okay, so here are 3 videos of that 8-link robot, which is fixed here. And there are 3 approaches, as I said. Okay, I'm not going to discuss these 3 approaches. There is something called modal approach, which was invented long time back. There is a pseudo inverse approach, which has been invented also long time back to resolve the redundancy. And this is our tractrix based approach. Okay, remember, I need to go from point A to point B in a plane. I need only 2 degrees of freedom, but there are 8 of them here. There are 8 joints. So let's see what each of these trajectories do. So I'm going to trace a circle with the tip. So there is a pen here which is attached. Okay, and then it will trace a circle on the floor. Okay. So the timing of the circle is same, the size of the circle is same, everything is same, but the calculations for each one of the joints are done differently. So here are 3 videos. So the tip is trying to trace a circle. Okay, so sometimes this jerky, slipping motion is not because of the algorithm, but it is moving on a floor, tiled floor. So hence sometimes this things slip. Okay, so that is not this jerky motion is not due to the algorithm, but it is due to the robot which is being moving. Okay, so what you can see, what is the most important observation? The first observation is this tractrix based approach is drawing a reasonably good circle. This is not so good and this is pretty bad. More importantly, I will play this and you can watch once more. In the tractrix based motion, to trace the circle, we want to move the furthest joint as much as possible first. Then when you cannot do it, then you move the joints which are closer to the base. Whereas in these other two, you are moving all the joints at all the times. So here you can see these joints are not moving, only these outside ones are moving. Okay. So after a while, you can see that maybe, oh, this third joint is now has to move. This one has to move. Then this one, and so on. Whereas this one, all the joints are moving. And why? Because in the tractrix motion, the idea is that the motion of the head and the motion of the bodies before that gets washed out. Okay, and it is a good idea because this motor has to move this long chain. Okay, so it needs to be very powerful, much bigger. This motor sees only the head. So if I am tracing a curve such that only the last few links are moving, then it is much better. We can use this tractrix based approach for hyper redundant robot where the base is not fixed. Okay, so here I am going to give some motion of this, again, this 8-link robot. I'll give some motion of the tail. So this motion is given like a sinusoidal motion, and we compute the motion of all these joints and then let it move on this tiled floor. So you can see what it looks like. Okay. So our claim was that this is a very natural looking snake-like motion. Okay, how many agree with that? People think it is natural looking snake-like motion?
Yes, sir.
Okay, so this is a robot which is very useful. Okay, of course it is very simple, crude prototype, but a robot like this with, let's say, the power supply inside this robot itself and all the sensors and computers and everything on itself, they can go into some earthquake place. Okay, so some disaster has happened, so it can go through narrow gaps and it can go and take videos and things like that. Okay, so there are many other applications of this Tractrix-based approach. Little bit of summary. This is very simple. It's a linear complexity algorithm. So if you have more links, complexity does not increase. It appears to be more natural as the motion is washed out. Okay, so I showed you the motion of the body of a snake with chosen head motion. Now I'm going to show you some few other just simple videos. One is I can use this Tractrix-based approach to simulate the tying of a knot in a thread. Okay, I'm going to discretize this thread into small pieces and then move either one end of the thread to tie a knot or another end of the thread to tie a knot. Okay, I will also show you some videos of this snake robot in a cluttered environment, actual simulated earthquake disaster area, and motion of a snake robot in a pipe. Okay, so suppose I have a pipe. These are all simulations. Okay, don't think that we have already created all these hardware. These are all simulations. We can also show you the same algorithms can be used to show the motion of an endoscope in a GI tract. Okay, how many of you know what is endoscopy? Okay, so sometimes these doctors, they will push something through your mouth to take pictures, okay, of what is happening inside your stomach, if you have ulcers or cancer or things like that. So we are going to simulate that motion. So one important thing before we do all this simulation is we need to make sure that there are no intersections between parts of the link. Okay. So this is a simple algorithm which says that you put a sphere around each link, and if these two links are hitting each other, then this D should be not hitting each other. So this D should be greater than L, and if this D is less than L, there is a collision. Okay, let's not worry about it, but we have to have an algorithm which makes sure that it is not colliding with each other. And when it is colliding or coming close to colliding, we move it in the opposite direction. So here is a video of a snake. Okay. So the head is moving. Okay, and again you can see it looks very natural. Okay, so when the head is moving, the tail is still straight. Okay, and this head is moving in 3D. This is the motion of a rope, and I'm tying a knot. Okay, as I told you that you can see these small spheres. I have discretized the rope into small pieces, and one end is moved. This is the motion when you have two ends which are moving. So you can tie a knot. Okay, demonstrate or simulate the motion of a rope tying a knot. Okay, if you think about it, it is not very easy to demonstrate that you are tying a knot on a computer. We can also do obstacle avoidance. Okay, so as I said, this Tractrix is an optimization problem. We are minimizing the linear velocity of the tail. Okay, and at every instant, the velocity is along the tangent in free space. We can modify that problem to include constraints. So if there is an obstacle, we don't move along the link, but we move perpendicular to the link. Okay, and we need to grow these obstacles a little bit such that although I am saying one middle point of the link is not hitting this obstacle, how do I know the rest of the link is not hitting? So we grow this obstacle. This is the standard trick to include the effect of the size of the link. Okay, so here is a video which shows this robot, okay, which is moving through this obstacle field. So there is this one circular obstacle, one sort of like a square obstacle, and so on. So I am giving some path of this robot, and I will show you that it will not hit any one of these objects. Okay, so this is happening in a plane. Okay, and the same thing is happening in 3D space. There is no problem. You can extend this algorithm to 3D space. And these are all done in MATLAB. Okay. So this is the work of Midhun. Actually, he is from Kerala. Okay, so this video will go on and on. So let's stop here. So basically, I can show you that this snake robot can go through this obstacle field. Okay, we also built a hardware. Now this time there were 12 links. So in order to move this robot on the floor, there are these motors or wheels which will drive it forward. Okay. Again, the commands were sent from a laptop to each one of these motors. So there is a lot of wiring. And we are going to use that obstacle avoidance algorithm that it will go perpendicular to the obstacle when it is close to it. So here is a video of this 12-link robot. Okay, so what you can see is there is this person who is walking, is carrying a laptop, and he's sending all these commands, and also power supply is there. So the robot could move through this obstacle field without hitting any object. Okay, and since we have done a lot of simulations, we can actually capture the images here, which is the real hardware images. And we also did this simulation. We can do these simulations. If you need to publish in some good journals, you need to do all this work. Okay, you need to show simulation results and then hardware results. So as you can see that this object and this object is looking very similar at these 3 instants of time. So there is a very good match between the simulations and the modeling that we have done and the actual experiment. Here is another video which shows a snake robot with many links which is moving. These are simulations. This is not hardware. So this is like a picture which is simulating some room with some pieces in it, and then there is this robot which can go through all these obstacles without hitting anything. Okay. And then maybe you can take pictures and send back the pictures. Okay. This is the other view. I should have shown both of them at the same time. So the idea is that we can use such snake robots for search and rescue in disasters. Okay, so we will be able to avoid all the obstacles which are there, and it can go inside a room or it can go inside this disaster area and send back pictures. We can also show this video where the same robot is going through some piping. Okay, so suppose you have this huge industrial establishment with lot of piping and we want to inspect them. At the end of the robot, there could be a sensor which is measuring some things, maybe if there are cracks or not in the pipe somewhere. And it can go through this piping and then take pictures. And final video in this whole thing is this motion of this endoscope. Again, simulated motion of the endoscope. So basically, these are actual images of a human being. Okay, this is not created. So this is a model of a human head, mouth, and the GI tract. GI tract means basically the way we eat. Okay, how the food goes into the stomach. This is a data set which is called Visible Human, which is available in the public domain. And we can show this endoscope moving through this GI tract. Okay, and this endoscope is modeled as a hyper-redundant robot. The initial motion is horizontal, and the later motion is, it will follow the middle of this tract. So this is actually the stomach. And again, the simulations were done in MATLAB. Okay. So in summary, a robot needs 6 degrees of freedom for general motion in 3D space. Many robotic and biological systems have many more than 6 degrees of freedom. These are called redundant systems. So we need to use this redundancy to optimize. We could use it to obtain isotropic velocity distribution. We can get natural motion. As I showed you, it helps in learning in a human hand. Okay, and it can do obstacle avoidance. Okay, so any question till now? Because this is the second topic which we will discuss.
So we would be displaying all queries at the end of the session, sir.
Okay, fine, thank you. Okay, so let's continue. So the second topic which we have worked on in the lab is something called sun tracking. Okay, so this is a way to harvest solar energy, and the idea is the following. So we have all these mirrors in a field, okay, and as the sun was moving in the east-west direction and a little bit in the north-south direction, we are going to move these mirrors such that the reflected beam, okay, the reflected sunlight is always focused at one place. Okay, so at that place, you can see all this sunlight is being focused here by all these mirrors. Okay, there are many, many mirrors in this field. So this is a picture from Spain, I think. Okay, and this is being constructed in many countries. It is in US, Australia, even I'm told people are trying in India also. So what we want to do is we want to track the sun and focus the energy at a distant receiver. So how distant is this? This could be nowadays as much as 1 kilometer. From this point to the last mirror on the field could be 1 kilometer away. Okay. What other challenges is there? We want to focus it very accurately. Okay. More important, the sun is moving very, very slowly. It moves only 180 degrees in 12 hours. And we need to have two-axis motion. We need to move the mirrors to track the sun in the east-west direction and also a little bit in the north-south, because with season, it moves north-south also. And we need very, very high accuracy. So 2 milliradians of pointing accuracy. So if you think of it, if you have a normal DC motor, which is rotating at something like maybe 600 RPM or 1000 RPM, okay, this is very, very slow compared to that. It is only 180 degrees in 12 hours, not even a full rotation in 12 hours. So hence, we need a very large and very expensive gearbox. And expensive gearboxes or large gearboxes also have friction and backlash. And then this accuracy will go for a toss. Okay. So we need to have some device which can move these mirrors in two axes, east, west, and north, south, and at the same time move it very slowly, and at the same time move it very accurately. So this is the challenge. So there are existing heliostats. So this is a heliostat, each mirror with all those DC motors and other things which can move this mirror, that is called as a heliostat. Okay, so there are existing arrangements to track the sun. There is something called as an azimuth elevation arrangement. So you rotate about a vertical axis and you rotate about a horizontal axis. So this, you can see if I rotate about the horizontal axis, it will track the east-west motion of the sun. Right? Likewise, I can have another arrangement which is called target aligned, which means there is a rotation of an axis which is inclined, or it is along the normal to the mirror, and then there is one more which is horizontal. So these are basically, if you remember, I had this, I don't know how many of you were there in the first half last month. So there is something called Euler angles, which describe the orientation of a rigid body in 3D space. So these are two sets of Euler angles. We can also propose a parallel robot which can do the same thing. And this is what the student did. He was Ashit. So basically what we have is a robot with 3 links, okay, 3 legs, sorry, and each leg is some spherical joint, a prismatic joint, and a rotary joint. Okay, so the mirror is mounted on this green triangle. There is a fixed base. And as the sun is moving, so this vector GS is pointing to the sun. Okay, GR is pointing to the receiver. The receiver is fixed. So as the sun is moving in the east-west or north-south direction, we have to make sure that the mirror normal bisects this angle. This is from laws of reflection. Okay, the incident ray, the normal to the surface, and the reflected ray must be angle of incidence is equal to angle of reflection. All these 3 vectors should also lie in a plane. Okay, so we need to, this R is fixed. Okay, so the reflected ray is always at the same place. As the sun is moving, we need to move this mirror normal such that these 2 angles are equal. So that is the task. And how we are going to move this mirror normal to this plane? By moving this L1, L2, L3, these 3 joints in the parallel robot. So here is some advantages. If you have a parallel robot, it has much more load carrying capacity. Basically, it is, the mirror is supported at 3 places. Okay, you can see the mirror is supported at 3 places, whereas here the mirror is supported only at 1 place. So if there is a wind, this mirror will deflect much more than this mirror. Okay. It has also more accuracy. However, there is one extra actuator. Okay. So if you have one extra actuator, this is a redundant system, just like for the hyper-redundant cases, those were serial robots, this is a parallel robot. Okay. So one way to resolve this redundancy is impose a constraint. In this case, we will impose this constraint that the center of the mirror stays fixed. Okay. So here is a video which shows how the mirror is moving as this black star, which is the motion of the sun, as the sun is moving in the east-west direction. So what you can see is very small. These are the legs of the robot, which goes bigger and smaller. The red line is the mirror normal, and the blue line is the direction from G to the sun. So as you can see, as the sun is moving, the blue line is moving and the red line is moving, but this other reflected beam is at the same place. We also did some finite element study of this mirror arrangement, because one of the claim is that we can support it at 3 places, and hence we can carry either a bigger mirror or the deflections will be smaller. So how do we do a finite element study? We make a model of a mirror, then we put all these backing structures which are made of steel ribs. Okay, and then you say that there is a wind load which is happening. There is also a self weight. The mirror itself is pretty heavy. Okay, it's like of the order of 10 kg per meter square. Okay, and then you do a finite element analysis with this wind loading and the self weight. Self weight is this vector, and it is mounted at 3 places. Okay, the wind load is calculated half CD rho V square, and we put a factor of safety which is 2. So what you can see is for wind speed of 10 or 22 and different sizes of the mirror, 2 by 2 meters or 5 by 5 meters, okay, the supporting structure that you want to make sure that the tip deflection is less than 2 milliradians, okay, we assume that we can live up to some deflection of the order of 2 milliradians. So we need a supporting structure which is like 20 kgs. Okay, if it is a 5 by 5 mirror, 5 meter by 5 meter, we need 1.3 tons, 1300 kgs in this azimuth elevation configuration, where it is supported at one place at the center here. However, when you have 3 RPS, which is supported at 3 places, the supporting structure goes down to 535 kilograms. Okay, so almost like 2/3. So what it is telling you, the supporting frame weight reduction of 15 to 60% if you use this 3 RPS robot, which is this. Okay, whereas if you use the azimuth elevation drive, in order to make it function, in order to make sure that deformations are not too much and the pointing accuracy is maintained, we need much more weight, and it costs more basically. So we built this robot, 3 RPS robot. Okay, we need to test it in the lab. Okay, in the lab there is no sun, so we basically invert the problem. Instead of the sun moving, okay, we have a laser which is pointed to the mirror, and as you move the mirror, the reflected beam will be at some path in the lab. So what is happening? We will assume that the sun is moving along the way this laser beam is pointed, and we are going to move the mirror such that the reflected beam is coming to this laser at this point. Okay, so here are 2 videos. So this is one. Oh, sorry. So this one is not working for some strange reason. Okay, doesn't matter. This would show how the mirror is moving. This is showing how the reflected beam is moving. And we marked all these points on the roof. Okay, and these points are basically the points for which the position of the sun would be at those places, such that the reflected beam will be here. So this is details of the sun tracking hardware which was built. So there are 3 legs, there are 3 linear actuators. This is the mirror, and there are these spherical joints which are obtained from scrap. And this linear joint has a motor inside through which you can power. Then there are these encoders which you can measure the rotations of the motor, and then you can find out how each leg is moving. Okay, so here is a video which shows these 2 mirror arrangements. I will come back to it a little later. And the reflected beam is shown on this roof, the water. So what we have here is one drive, which is one vertical motor, which is this one, and there is a horizontal motor, which is this one. So this is the azimuth elevation drive, and this one is the 3 RPS arrangement. So, and there are these 3 legs, and there are these 2 laptops which are controlling this motion. So ideally, if you have placed all these mirrors and controllers and everything properly, both these images should be at the same place. Okay, remember the idea is that the reflected beam should be all at the same place. Hence, you will get a lot of energy there, you will get high temperature there, and you can run a thermal engine there. So, but since this was made by students, it is not really exactly pointing at the same place, but reasonably close. And as you can see, at sometimes it is closer, sometimes it is a little far away, and that is because some problem with controller. Okay, so let's see it once more. This star shaped is because there is some deformation on the surface of the mirror. Okay. So what I am showing here is that both these heliostats, the azimuth elevation drive as well as the 3 RPS drive, they are tracking the sun and focusing the beam on this surface on the roof of this building. Okay. So in summary, I showed you both this 3 RPS and the azimuth elevation can track the sun and focus the beam onto the surface of this water tank. Okay. The errors are slightly larger because these have been made by students. So remember, we want like 2 to 3 milliradians, but this is like 10 times more. This is 20 to 30 milliradians. And the main problem is because of manufacturing and initial setting. Nevertheless, it's a very good proof of concept that I can have a robot, parallel robot, 3 RPS parallel robot, which can track the sun and it can serve as a heliostat. It can focus the beam onto some receiver, okay, and there I can convert the energy. We also built one more robot, parallel robot. This is the 3 UPU parallel robot. I don't want to go into too much detail, but basically there is again a linear drive. Then there is but this linear drive, there are joints here are not spherical joints. This is a hook joint here and this is another hook joint here. And the axis of the hook joint are such that they meet at one point. So this is called as the fixed point. Okay, this is a point which is in 3D space. So you shift the mirror up to this point, and it turns out that this mirror will rotate about this fixed point. So this is like a wrist. Okay, so in a serial robot, we have a wrist. So the end effector can rotate about the point of intersection of the wrist or some point in the wrist. So in this case, this mirror can rotate about this fixed wrist point. And as a result, this robot can be used either in the AZEL mode or the target align mode. Remember, AZEL is 2 rotations, vertical and horizontal. Target aligned is 1 normal to the mirror and 1 horizontal. So basically there are 2 rotations in each, and I can do both these 2 rotations, either azimuth elevation or target aligned configuration, just by running different software, because it is rotating about this fixed point. Why do we want to do it? It turns out that the target aligned and the azimuth elevation configuration behave slightly differently, not much, some 2 to 3% difference in the form of how much of the projected area is outside the receiver. Okay, so what you can see is if this cyan is the receiver, the azimuth elevation is this dark blue, and this target aligned is this red. So at 12 noon, the target aligned is this red square, which is the projection of the mirror onto the receiver, whereas the azimuth elevation is this. So as you can see, the red is slightly outside here, but at some other place, the blue is slightly outside here and the red is inside. So at different times of the day and different times of the month, okay, different months, okay, the target aligned is little bit better, and at some other times, the azimuth elevation is a little bit better. Okay, it's not very much. It is like 2 or 3%. But even then, when you are collecting energy, even 2 to 3% makes a big difference. So, and in this case, we can switch between target aligned and azimuth elevation just by running software. So in this figure, we are showing you for the March equinox, what is the area which is lost, okay, when you have azimuth elevation, which is some little bit more here, but most of the time less. Target aligned is more here at between 2 and 4 in the afternoon. Similarly, in the December solstice, the azimuth elevation is more losing in the morning, but target aligned, you lose more area in the afternoons after some 10 o'clock or something. Okay, so we want to switch between these 2 configurations so that we make use of the least spillage loss. Here is an example of this robot which we built, of this heliostat which we built. So at 3:18 p.m. we have this azimuth elevation configuration. So this is from this computer somewhere. We are driving this mirror using this azimuth elevation configuration. In a few minutes, we run a different program, and this is the target aligned configuration. So as you can see, that the mirror configuration looks different, but the image is more or less at the same place. Okay, so what are we claiming? We are claiming here that we can switch between AZEL and TA configurations just by using software. There is no hardware changes. So in summary, we are using a novel parallel manipulator, a novel use of a parallel manipulator for sun tracking. There are lots of kinematics and design challenges to build a heliostat. Most importantly, it needs to be very accurate and it needs to move very slowly. Okay. A parallel manipulator has many advantages. It can carry more load. It can use low-cost linear actuators. Okay, I don't need a gearbox. So as you see, in all these, there are no gearboxes. Whereas in this configuration here, no, there is a big gearbox here. In this motor, there is a gearbox. So this motor costs maybe $1 lakh with the gearbox. However, these are much cheaper. These linear actuators are much cheaper. Okay. Potentially, a parallel robot is more accurate, and it is also e-reconfigurable. Okay, why? Because we have a redundant actuator and you can switch between various modes. As it turns out, the hardware which was developed is not really more accurate because there is too much play at the joints and we need to do better manufacturing. Nevertheless, it's a good proof of concept. Okay, so this was the second research area in our lab, and the rest of the talk I will show you a third research area which students are working on. Okay, so I need about 20 minutes, 25 minutes, so I think we have that time. So basically what we have is we want to extend our knowledge and use of snake robots to endoscopy. So endoscopy means that this is a sketch of a human body. So we insert this long flexible tube with instruments and controls. It is inserted through the mouth into this GI tract. It will go there and we can take pictures. Okay. So what does this endoscope look like? Basically, it's a long flexible tube of the length of the order of 1.5 meters. There are these controls. There are two of these switches or two of these knobs which you can rotate, and as a result the tip of this endoscope can rotate in 3D space. So there are cables running through this tube, and as you rotate this it will move in one direction. As you rotate this it will move in the other direction. There are also these two ports, okay, where you have water and air. So as you are pushing this device through your mouth and into the GI tract, if there is any food or something, you can remove that food by squirting water or air. There is also one more port which is called the biopsy port. So basically you can push in another small thin wire which can be controlled by pulling or pushing here through this tube, and this is shown here. So at the end of the wire you can have a small forceps, you can have a small scissor, okay, which you can take some samples from inside your stomach. You can check whether it is cancerous or not. So this whole end here, okay, this whole end is of the order of 12 millimeters. There is a lens and a light which is of the order of 5 millimeter diameter lens. So there is a camera and there is a source of light using some fiber optic cables. And as I said, there is an air and water jet. And then you can push in these through this biopsy port, one small device where you can take some samples. Okay, so this is done in many places nowadays to check whether you have any problems in your stomach. So the doctor or the technician will take pictures and then the doctor can decide what to do next. Okay, so as I showed you, while this motion is happening, you are going to also insert this biopsy, and we want to do it very accurately because we want to take samples from a place which is of interest. But when you are trying to position this biopsy device, okay, the whole head moves and the camera view also changes. In addition, this tube is very low stiffness. So when you are trying to position it, it is not very easy to position. Okay, so there is very little control in positioning the tip of endoscopes or the forceps. But we need more control. We need to position it accurately to take samples. There's a lot of skill required. And more importantly, we have only a few minutes to do the whole thing. Because if you are keeping a tube inside your body, through your mouth, you cannot keep it for half an hour because then the person will start gagging, okay, and they react and they vomit and so on. So there is very little scope of surgery. Right now, it is primarily used for diagnosis and you can take some samples. But what we wanted to do was, we wanted to have independent control of the forceps without moving the entire endoscope. Okay. So if you want to move that small 3 millimeter long 3 millimeter wide diameter, you need very, very small actuators. Okay. One possibility is SMA wires. How many of you know what is SMA? It is called shape memory alloy. So in a shape memory alloy, what happens is if you heat it, it will contract. It will change its dimension. And hence, you can use it to actuate some device. It takes too long to heat and cool. We can have very small motors, but these are very, very expensive and complicated. Transmission is required. The motor has to be outside, and you have to send it through some cable and wire and so on. And it is like 1.5 meters long. So it is not very easy to do. About 5 millimeter is available for whatever you want to do. The advantage is that the tip needs to move in a very small region. So roughly about 2.5 centimeter diameter sphere, but we need to move fine motion control. So inside the stomach, there is not much space. So that is one advantage. And the other big advantage that we have is we have camera sitting there. So you can have visual feedback. So if you are not going to the right place, you can change your motion and you can correct it. Okay, so we proposed something called as a miniaturized pneumatic air muscle. So basically it is a very thin tube which is made of silicon, but it is braided with some nylon wire, okay, in a particular way. And this, due to this tube and this braiding, if you pressurize it, it will contract. And it will contract up to 20% of its length. So initially, if it is L0, it will become LF. Okay. So initially, this is D0 and L. So this end is tight. When you pressurize it, it will contract. And so hence it is like a muscle. Normally muscles in your body, they contract when you energize it somehow. So this is why it is called as a miniaturized pneumatic air muscle, because it is actuated using pressurized air. So here is a video which is showing you how this muscle will contract when it is pressurized. So there is a small weight which is attached to keep it straight, and the student is going to apply air pressure using a normal syringe. So it is not a very, very high pressure, because you can see a syringe does not do too much pressure. So please watch the end of this muscle, okay? So when you release it, you can see it is moving. Okay, it is moving. You can see slowly, not much, but it is moving. So you can, as you release the pressure, you can see. Okay, good. Yeah. Okay, fine. So you can see it is moving. Okay, and it moves about 20% of its weight, of its length. So we made a model of this pneumatic muscle. There are already some existing models, which is by some Schult and Shao, Hannaford. There is a model by Liu and Ran. There's a model by Kothera. And then we derived our own model. Okay, so this inverted triangle, cyan color, is our own model. This green is a model which is by Chu and Hannaford. Okay, this blue is by Liu and Ran. So what you can see, and this black are these experiments. So whenever you do experiment, there is a mean value. We do experiment several times, and then there is a bar around this experimental data. So what you can see is this inverted triangle is model contained. So this is for length of 40 mm. This is for length of 60 mm. in both cases, our model is very close to the experimental data. So this model contains a thick cylinder model. The boundary conditions are changed to model the braid. Remember, the silicon is very soft, but the braiding is quite hard. So the braiding does not move. Okay. The contact area with the braid is not very easy to obtain. So we will use two experimental data points to determine the parameters related to the contact area. And as I showed you, this experimental results match the model reasonably well. Why do we need a model? Because later on we want to use the model to control the contraction of this air muscle. Okay, I am going to use this air muscle at the tip of this endoscope to move something. And in order to move something, I need to know a relationship between this movement and the pressure which you are applying. And for that, we need a model. So what is our device? The device is that there are three such air muscles. There is an interior spring and there is an outer spring. These internal and outer springs are used to bring it back. Once it has moved, how do we bring it back? So it helps in moving back. Okay, and we arrange these three air muscles, okay, in 120 degrees apart. So if you can see that if two of them contract, the resultant motion is along the common bisector of that two angle. Okay, so by either contracting one or two or three at a time, I can move this end, which is this tip, which could be some kind of a device on a surface of a sphere. Okay, we can also vary the pressure, and depending on the pressure, it contacts more or less. So I can move not only in one direction, but I can move more or less in that direction by varying the pressure. Okay, this is the developed hardware. We wanted it with less than 5 mm. We could not do it. So this was like about 7 mm. This is between 6 and 7 mm. Okay, and this is that grasper. So basic idea is that we have these tubes which are running through and which we will supply air pressure to these muscles, these braided muscles. Okay, this distance is about 4 centimeters, 40 mm. And depending on which two you pressurize, so if I pressurize this will contract, and hence this tip will move in this direction. Okay, if you pressurize these two, it will move in the perpendicular bisector direction. Okay, and once we have this motion, we can make a model, and depending on those three contractions, we can see where the tip is. Okay, and there is a very well-known model called elephant trunk model in kinematics, which tells you that if I move each one of these muscles by X amount, where does the tip head go? Okay, so we did this model using this elephant trunk model in kinematics. We actuated 1 or more NPM at the same time, and then we showed that the model predicts the location of this tip with experiments with an error of less than 5%, okay, which is acceptable. So this is a picture of one of those experiments where we have energized maybe this last muscle here, hence the tip will move downwards. We also have elephant trunk model, which will tell you how much the head will move, and this error is less than 5%. Okay, here are two videos which will show this device which is moving. So as you can see, there are these plastic tubes which are supplying the compressed air. At the end of this device, we have put an LED just to see it more clearly. There is a scale here which tells you that it can move between 0 and 30 mm. Okay, and it is in all directions. I'm going to show you one which is front view and one which is side view. So front view, you can see it is moving in all directions. And in the side view, it will go up and down. Okay. So as I said, we don't need to move much. Okay, we need to move a maximum of about 2.5 centimeters. So, and that was achieved. So this motion, although not shown here, all these tubes is taken to an air compressor, and there is a controller which is a joystick, and this, when you move the joystick, the air pressure will go into one or more of these tubes, and depending on how you move the joystick, the end of this catheter or an end effector will move. Okay, so if you move to the left, you can program it such that you can see some realistic motion of the end effector when you move this joystick. So I'm not showing you the rest of the control system, but there is a processor, there is a compressor, air compressor, there is a place where the compressed air is stored, and then there are these valves. There are several valves which are used to send the air to each one of these tubes, and so on. Okay, so this video will go on and on. I don't want to show any more, but basically just by applying air pressure, I can make this end move, and you can see the motion of the head. The last topic which I want to very briefly touch, because this is an ongoing work. So instead of air muscles, we can also use cables. Okay, so this is showing that you have this flexible backbone which was 3D printed. Then there are these discs through which you pass one wire, very thin wire. So when you pull this wire, this thing will bend. And again, as usual, we have to make a model which shows that if you pull by some distance, how much the head will move, how much this end will move. So we have created a model for several kinds of cabling. So this is a straight cable. So as you can see, it is straight. But we can also have a cable which is twisted, which is called a general cable routing. And these dots here show our optimization-based model and some existing model, which are called as the Coserot rod theory. Okay, so we can see that we have connected a wire, pulled the wire, and showed that how it is moving. Then you take a photograph, then you use a camera to see where these points are and compare. And this is a video of this experiment using these 3 such fingers. Okay, and these 3 fingers, each one of them has cables. Okay, and we can control the motion of the cable, and we can grasp and move these whatever is grasped. So in this case, it is a spherical ball. So as you can see that there is a cable which is running through this thing, and so intentionally we have made one see-through transparent, but exactly 2 same things are here. So as I pull this cable, you can move this cube, and you can rotate the cube, you can position and orient the cube. Okay, so this is a work which is still continuing. we need to make it much better. We need to predict the motion much better, and so on. So in conclusion, we'll stop here. I've showed you some 3 areas in which our lab is working on. So basically, one is to do with redundant robots and human arm. So in a redundant robot, we can use optimization. I showed you that redundancy helps in adapting to perturbation. I can use something called as a tractrix based algorithm, which gives natural looking motion. I can show you how to simulate the motion of a snake, tying of a knot, or this endoscope moving through the GI tract, and at least they look very realistic. The second area is sun tracking using redundant parallel manipulators. It is expected that they will be more accurate, they will have less structural weight, the cost will be less, and so on. The third area is this actuated flexible endoscopic end effectors. We can either use pneumatic air muscles or we can use flexible cables. Okay, so thank you very much. So if there is any questions, you can send me email or you can look at these websites. So this is the end of the talk.
Thank you so much, sir. We would be posting queries on screen right now, sir. Could you please stop sharing your PPT?
Yes, I will do it. 1 minute. Let me see how to do that first.
Sure, sir.
Okay, I think I have stopped sharing. Can you see your screen?
Yes,
I can
sir.
see.
Yes, sir. We would be sharing now.
Okay.
Sir, are you able to see the questions on screen?
Yes. Yes. So while designing, developing, and building a robot, what are the basic things that we should take into consideration, which involves moving mechanical parts? Does the precision of the robot increase when we add more degrees of freedom while making more joints? Okay, the answer to the first part is there is a lot of issues when you need to design a robot. So there are workspace issues. How big is the workspace you want? Where all do you want to reach? What is the maximum and minimum velocity? And so on. Many issues are there. You need to read a book on designing robots. Okay, so there are many chapters in many books which discusses design issues. Does the precision of a robot increase when we add more degrees of freedom? No. Okay. So because you are increasing complexity, the controller complexity increases. However, the flexibility of doing a task is better if you have more joints. Okay, so I can, as I showed you, simple example of you touching your nose. I can touch my nose in different ways. So suppose there is an obstacle, so I cannot reach my nose in one way, I can reach it in some other ways. So adding more joints, adding more degrees of freedom increases the flexibility of doing a task. Okay. Sir, what are the applications of muscle fiber that you showed you? So as I showed you, these are very thin, small actuators. Okay. And these actuators can be used in any place. Okay. These actuators can be used in many places where you need thin, fine actuators. Despite unparalleled biomedical expertise, why India could not make impact in diagnosis and therapeutics in COVID-19? I don't know. Okay. I am not a biology or a doctor, so I don't know the answer to that question. Next, any other question is there? I can see 3 questions.
Yes, sir. Participants, do we have any more questions coming up? You can unmute yourself and please ask. So I think we don't have any more questions.
Okay, good. So thank you very much, Deepa, and thank you very much for inviting me. I hope this presentation was useful, and at least you get an idea of what kind of research is happening in ISC in our lab. There are other labs in India, in IITs and other places, where various kinds of research is happening. So okay, so anybody who is interested in robotics or research in these areas, you can contact me as I showed you the email ID and the web page. Okay, thank you very much. If there are no other questions, I want to leave now.
Yes, sir. Thank you so much. I must mention our deep sense of appreciation for Dr. Ashitava sir for giving an excellent coverage on various projects at IIC Bangalore. We are truly humbled by your insightful contributions to this STTP. Your presence here has definitely enriched the session, and for this we remain grateful, sir. On behalf of the Department of Electronics at TIST, I once again express my gratitude for your presence, sir. Thank you so much.
Okay, thank you very much. Bye.
Thank you, sir.
Dear participants, we have posted attendance link in the chat box. Kindly note that participants would be issued with certificate of participation only if they attain an attendance percentage of 80% and also score a minimum of 60% marks in the online test that would be conducted at the end of the STTP. We would resume the session at 1 p.m., the next session. We once again remind you participants that today is the date for submission of topic for the project activity regarding the STTP.
Ma'am, can you please share the link of attendance?
Ma'am, it has already been given in the chat box.
Ma'am, it's not visible, ma'am. Due to my network was low, so I rejoined again.
Okay, sure. We would be sharing it once again in the chat box.
Thank you.
Attendance link has been posted in the chat box. Thank you so much, and we'll resume the session at 1 p.m. Good afternoon, Jisha, Miss.
Good afternoon.
Miss, we'll begin the session shortly.
Okay.
Meanwhile, you can test your presentation, ma'am.
Okay. Can you see the presentation?
Yes, Miss, we can see. Ma'am, do we have any videos attached to the presentation?
No.
No, okay. Okay, ma'am.
Now,
It's
can you
coming
see
well.
the screen?
Yes, ma'am, it's coming well.
Okay.
We'll begin shortly, ma'am.
Okay.
Good afternoon, all. Welcome back to the second session for the day. For the second session, we have Dr. Jisha VR, Associate Professor, Government Engineering College, Thrissur, Kerala, and she would be dealing with the topic Mobile Robotics with MATLAB. Ms. Jisha VR joined College of Engineering Trivandrum in 1999 after obtaining BTech in Electrical and Electronics Engineering from College of Engineering Trivandrum in 1995. Subsequently, she acquired MTech in Control System from CET and PhD from Indian Institute of Science, Bengaluru in 2012. After 20 years of service at CET, she is currently working as Associate Professor in the Department of Electrical Engineering, GEC Thrissur. She has around 25 publications in international conferences and journals to her credit. She is also officiating as Chair, IEEE Robotics and Automation Society, Kerala Section, Member, Board of Governors, Kerala Technological University, and Convener, Syllabus Committee, BTech Robotics and Automation, Kerala Technological University. We welcome you, ma'am, to handle the session.
Thank you, organizing team, for inviting me to the session. But before I start, I would like to know whether the participants for phase 2 are same as that of phase 1, or they are different. They have the...
No, ma'am, we have different participants too.
They are not common actually. Okay.
We have common people too, but we have additional participants too.
Okay, so I would also like to know the background. Is it a mixed background from electrical, mechanical?
Yes, ma'am. They are from different backgrounds.
Okay, okay. So, good afternoon once again, and hearty welcome to this session on mobile robotics with MATLAB. I'm not sure whether you are aware of this MATLAB platform. How many of you are not at all aware of MATLAB platform? Can you just share a message in chat box? Is there anyone? Yes, I could see the response from hello Vasudev. Okay, so anyone who is not at all aware of MATLAB, or at least I think you might have worked with MATLAB. Some simple examples. Okay, so I hope that you all have, yes, hello Vasudev, I hope that you all had some background in MATLAB, and I also believe that you have some basic idea of robotics too, because already so many sessions of this FDP are over. So I think that you have those prerequisites. So with that introduction, let me move on. Can you see the presentation?
Yes, ma'am, it's visible.
Okay. So this is the topic of discussion today. So how can we start working with MATLAB, or how can we start the simulations of mobile robots with MATLAB? So that's what we are going to see in today's session. So this is how I have scheduled my presentation. I'll just give a brief idea on mathematical modeling and also some basic idea of model-based control. And I will also be discussing about modeling of a differential drive robot, because those who are those who have started working with robotics know that the simplest model to get started is a differential drive configuration. And then once you are confident with that model, you can take up complex models of maybe omnidirectional robot or a steered robot or any robot like that, or even a humanoid robot. Humanoid is somewhat different because it is an extension of manipulators and all, where the transformations and all are very, very important. And the topics which are shown in blue are the programs which we are going to discuss today, the MATLAB programs which we'll be discussing today. Okay, so before moving on to the original session, I request all the participants to unmute their mics as and when doubts are arising, because otherwise the session is going to be really monotonous. And I know it's a post-lunch session, and there's a very good possibility that you may sleep in between. So I wish that at least whenever you are having some doubts in your mind, please unmute and ask, because no chat box I won't be able to see. Okay, so I will start with some pictures of the robots you are familiar with. Okay, so hope you all are aware of these robotic configurations, right? So this is basically a humanoid robot by Honda, very famous humanoid robot, but it is a very complex robot with more than 50 degrees of freedom. Hope you know what is degrees of freedom. Degrees of freedom means the number of independent movements possible. So the number of independent movements possible are more than 50 in this robot. And this is a typical robotic manipulator which is used in robotic industries. If you take the worldwide population of robots, industrial robots are dominating. And this is an example of a mobile robotic platform, which is actually moving on wheels. Okay, so you might have seen mobile robots with 4 wheels or 2 wheels or 3 wheels and more than that. There are different configurations possible. So we'll see some of the simple configurations. So this is actually a legged robotic configuration, which is a hexapod, which is having 6 legs. Okay, so if you look at the characteristics and the analysis perspective, see the humanoid robot you can consider as an extension of this manipulator, because it is having so many links and interconnected joints. So similarly, if you look at this robot configuration also, there are so many links interconnected by so many joints. But the thing is that here the base is fixed, but in this case the base is not fixed. So correspondingly, the frame assignment and the coordinate transformations will be slightly complex when we compare this robot compared to this one. And if you look at this configuration, hexapod is also, you can see it is having links and joints, but in this case also the base is not fixed, it is moving, right? So the analysis similar to this may be required if you wish to perfectly design robots of this sort. And this is another category of robot, which is a flying robot. Okay, so these are the different category of robots which we wish to work with, or which we wish to design, right? Okay, so among all these configuration, to get started or to start designing is this configuration, which is actually the mobile robotic configuration. Because even with 2 motors and all, you will be able to build a very simple robotic configuration. Okay, but all these things will require some more understanding of kinematics, dynamics and all. Then only you will be able to design those combinations which are capable of doing the desired tasks. Okay, so we will be mainly concentrating on the mobile robots which are moving on wheels. See, mobile robots itself, there are different. See, if you look at this one, this is also a mobile robot, right? It's moving, but it's moving on legs. But if you consider this also, this is also moving, but it is also moving on legs. But this one is moving using wheels. Okay, so in this session, we will be mainly concentrating on mobile robots which are moving on wheels. Okay, so for easier understanding, I have taken only that configuration. And next, I will just tell you about a mathematical modeling. So actually, I have taken a session on mathematical modeling in the phase 1 of this robotics course. So those who have attended that will be remembering what is the necessity of mathematical modeling and how to do the mathematical modeling. Okay, so what we need in case of mathematical modeling is just the input-output relations of the system. Okay, so we need to just have an input-output relations of the system. So generally for maybe I will take an example and then I'll go back to that slide. For example, if you consider a car, okay, so all of us know how to drive car or scooter, all of us are aware of that, right? So when you consider a car, have you ever thought, okay, what are the inputs we are giving to the car and what are the outputs we are getting from the car? Okay, so these kind of thought is required if you wish to make the car autonomous. Okay, so all these detailing is required if you wish to make it autonomous or semi-autonomous. See, whenever we are trying to build robot, we may build them as semi-autonomous ones or autonomous ones. So in those situations, we may have to look at these systems and ask this question, okay, what are the possible inputs and outputs if you consider this car? So while driving a car, what are the inputs we are giving? Can anyone answer that question? Which are the inputs? See, generally when we are driving car, what are the things we do? I will be applying force to the accelerator pedal, right? Then sometimes I'll be applying force to the brake pedal, and also I will be moving the steering, right? These are the main things we do, right, while driving. Okay, and depending on these inputs, the car will move forward. So with this introduction, can anyone say what are the inputs? Have you ever thought what are the inputs and outputs if you consider car as a system? Have you thought in that way? Can anyone say? Because if you wish to make a system autonomous, then you have to ask this question. See, if you just wish to move it by means of some mobile phone control or some remote control, then no, you don't need that. But we need to think in that perspective, right? We wish to have. So all of you are aware of Google car, right? So it is an autonomous vehicle. So all these things come to our mind if we have to make the system autonomous or the car autonomous. So can anyone tell me what are the possible inputs? Because only if you know that, only if you think from that perspective, you will be able to apply model-based control. Anyone? Any mechanical engineers in this session, attending this session? All are sleeping. Come on. Any mechanical? No one, all are sleeping. Heavy lunch. See, otherwise it will be really boring. See, if I talk monotonously like this, no, it will be really boring. Can someone answer? See, I have already given the hint, right? What are the inputs I am giving while driving? Ashita, I could see Ashita Jose. Can Ashita answer to my question?
Okay, ma'am.
Mm.
The inputs we give gear shift.
Gear.
Steering wheel.
No, first gear, yeah. When there's speed change, we change the gear.
Okay.
But which are the inputs we give?
The first thing we give.
We give acceleration, right?
Okay,
acceleration
okay.
input, right?
Apply brake. Okay.
Accelerator, we apply the brake
Yes.
pedal. We press.
Yes.
Then
steering control.
yes. So these are the steering. Okay, so there is accelerator pedal. So we apply the acceleration as well as we apply brake. That's the second input. And third input is the steering input, right? So I think someone has responded. Steering wheel control and output change direction of motion. Okay, well, not only the steering wheel. See, we are changing the steering in order to turn left or right, respective for getting the respective turning. We will be changing the steering wheel. But to move forward, we apply accelerator pedal, right? So these are the three inputs which we give to the car. So I have identified. So because why I am identifying that? Because I wish to make it autonomous. So if I have to make it autonomous, see, automatically I need to give all these inputs. So that is why I am trying to identify which are the inputs. Okay. See, automatically by means of some controller, I have to give, okay, what force should be applied to accelerator pedal. What force should be applied to brake pedal, and what should be the steering angle. At each instant, I need to give those inputs automatically, right? Then only the car will be moving on its own. So all these things we are giving manually. So instead of that, if you are making it autonomous, some controller has to find what are the inputs to be given. And what are the outputs what are the desired outputs we need from a car? It may be the desired speed of a car, desired forward velocity of a car, right? The linear velocity of the car, the angular velocity of the car, right? So, or even the X, Y, theta position of the car, right? So, this is the case when we consider a car. Okay, so if you look at this case, so I will be deciding in which direction the car has to move. It has to move forward or it has to take a turn. So I'll be giving inputs to the steering input. I'll be giving also acceleration and brake. Okay, so these are the inputs I give to this. Okay. So similarly, if you consider a mobile robot, okay, so if you simply consider a motor, we say it is actually if you simply consider a motor, that's a very simple system, right? A motor, if you consider, what is the input you are giving? You give an applied voltage and you will get output the required speed. Okay, so in this way you need to think, okay, what is the input I have to give and what is the output I am getting? So if you consider a mobile robot, Okay, so in now can you think, if you consider a mobile robot, so if you consider a robot like this, see, there are these are two wheels. There are 4 wheels, 1, 2, 3, 4. Hope you could see that. And these are actually steered wheels. And like our car, it's a car-like robot. Okay. So what all inputs we give here also, some steering angle is given. So in addition to that, we will be running the motor which is attached to the back wheel. Okay. So if you consider a very simple robot, very simple robotic configuration with mainly 2 wheels driven by motor 1 and motor 2, and there is some caster wheel for support, because 2 wheels configuration, see 2-wheeled configuration, which is unstable configuration. So what we do is we will put a caster wheel at the front. So there can be 2 caster wheels or 1 caster wheel for support. So this is basically for stabilizing the vehicle. Okay. So if you consider a mobile robot with 2 wheels, the inputs will be, what are the inputs? The motor speeds. The motor speeds or velocities. Is it motor velocity for right and left wheel? Okay. You give motor velocity of right and left wheel, and you will be getting the desired x, y, and theta for the robot. Okay. So in this way, what we need to do is, we need to think, okay, if I decide to work with a robotic system, what are the inputs and what are the outputs? So if you go back to this configuration, see, this is a quadcopter, right? This is a quadcopter. So if you look at this, what are the inputs? There are 4 motors. Quadcopter means 4 motors. So I will say that the inputs are omega 1, omega 2, omega 3, omega 4, the speeds of this vehicle, and the output decide will be maybe x, y, z, as well as pitch, roll, and yaw angles of the vehicle. Okay. So similarly, if you look at this, so there are 6 joints. So I think here there are 6 motors. Along with that, there are 6 motors here. So how many motors are there? All those motors are to be actuated. So it will be the position of those motors which are the inputs, or the velocity of those motors which are the inputs, and the output will be the desired x, y, theta, or x, y position of this hexapole. So similarly, if you look at all these configurations, we will be able to think in this perspective. So if you look at this robot, so it is having so many motors. So at each point of time, what should be the position input, right? At what angle we need to rotate these motors so that I get a desired end effector position. Okay. So in this way, we will be able to, you need to think in that way. Okay. So generally we are not thinking in that way. So only if you think in that way, you will be able to arrive at equations of this sort. Okay. So what we need to do is identify the inputs, identify the outputs, and then what is the relation between the input and the output. So that's what we have to do. So when you do so, you will be able to start with, first of all, a set of differential equations, and then from that you will be able to derive the transfer functions or the corresponding state space models. Okay, so it will be either in this form, which is a state space model, which is x dot equal to ax plus du, and y, which is the output, is equal to cx plus du, if the system is linear in nature. But sometimes the system may be non-linear, then you will be getting a relation as x dot equal to f of xu and y equal to h of x. The output is equal to h of xu. So if you look at this now, here what we are trying to do is, I need to see whatever system you take, see which are the inputs here. See, in this case, the inputs are in this case, use the input. Okay. In this case, use the input. So you, and the outputs, we will be representing at the Y part. Okay. So here also, even the system is non-linear, use the control input, and in Y, we'll be giving maybe X, Y, and theta of the robot. Maybe X, Y, theta of the robot, or X dot, Y dot, theta dot, and similarly, yaw, pitch, roll of the robot, because if it's a flying robot, we may have to consider all those things. So why we have to do all these things means, if you have to do precise control, you may have to do that. See, otherwise otherwise also you will be able to control that, but that is going to be trial and error method. So what I feel is that engineers are not supposed to do a trial and error control of different systems. So they should know, okay, what should be the input to be given, so that, okay, my car can be taken from point A to point B, or my mobile robot can be taken from point A to point B, or my manipulator can pick an object from point A to place it at point B. So I will be fixing all those waypoints, and I will be able to design a robot which will be capable of doing all these tasks. Only if you consider all these things, you will be able to proceed in that way. Okay. So this was just an example case I was just mentioning. So for all these, the final modeling is basically kinematics or dynamics. So all of you may be knowing what is kinematics and dynamics by this time, I think. So kinematics means it is the analytic study of geometric motion of robotic arm without considering forces and moments. And dynamics is with considering forces and moments. So depending on the scenario, we may have to decide upon which model is required. So sometimes the payload will be less. Payload, if payload is less and the speed of movement is less, then with kinematics we'll be able to manage. But this is to be considered if payload is more and if it's moving fast. Okay, so then you may have to consider dynamic modeling. Okay, so you may be knowing how to derive a kinematic modeling, how to derive the kinematic model as well as dynamic model. So with all those ideas, you will be able to start working with different systems. So if you're taking very simple model, so you need to just start with very simple model. That's it. You don't have to take a very complex model. Okay, and now I move on to the control part, which are the main steps when we design a controller for a particular task for a robot. So if you consider a manipulator or a mobile robot, what we do first is we'll try to get the input-output relations either in transfer function form or a differential equation form or a state space model. So now what we do is we look at those equations and see, okay, my system is linear or non-linear. Okay, so if it is linear, what I do is I will go for some P controller, PI controller, or a PID controller. But if my system is non-linear, the corresponding control, maybe if it's feedback linearization controller, I can use, or some sliding mode controller, or some SDRE controller. Depending on the model type, I'll be able to design a suitable controller, and I'll be able to make the system autonomous. So if you wish, see, at any point of time, if you wish to design an autonomous robot, you have to execute all these steps. But if you decide as an engineer to do things by trial and error, then you don't require this. But the thing is that if you have to if you ask the robot to move from point A to B, it will be maybe moving from some P to Q. So that's what it is going to show instead of moving from A to B. So if you wish to do all those specific tasks, definitely try to start from a model and then you design a controller for that. Okay. And some more details of model-based control. So how does a typical model-based control block diagram looks like? So what we do is we'll start with the robot model or the system model, and we, depending on the model, we'll be designing a controller, and depending on the model, we'll be designing a controller, and we'll be giving specific input parameters. So whatever is the input parameters, the desired input parameters we'll give, and the sensors attached to the robot will be giving you what are the actual values, and you will be having the reference. You compare the reference and the actual value, you will get the error, and which is fed to the controller, and controller will be actuating or giving input to the actuators, which are generally motors, right? It can be electric motors, hydraulic actuators, pneumatic actuators, depending on the type of robot model. Because now suppose if you consider robots which are used in car manufacturing industry, okay, so there no, you cannot use electric motors for the manipulators, okay, for driving the joints. So in those scenarios, you have to use hydraulic actuators, because now the payload is going to be car, very heavy. So then you have to go for hydraulic actuators. So here the actuators will be hydraulic actuators. But if you go to some food manufacturing industry or food processing industry, so there cleanliness is very important. So you cannot use hydraulic actuators. So there we go for pneumatic actuators, right? So so in those situations, the actuators may be pneumatic actuators. And for other scenarios, we may be using electric motors as the actuators. Okay, so this is a typical mobile robot control example or controller block diagram. So suppose you have a mobile robot model with you. What you need to do is you give a reference. Okay, so the reference here is taken as XY position. See, I am currently at the entrance of a particular room, and I need to reach the right corner of that room. So I will mark the right corner of the room as the destination here. And if I look at XY, I am currently at the entrance of the room. So XY is the current entrance of the position of the door or the entrance of the room. And this is actually right corner of the room. So what it does is, so in the feedback loop, actually there will be a sensor. Okay, in the feedback loop, there will be a sensor which will give this XY positions. So XY positions are to be known. So definitely without sensor, you won't be able to know that. So the difference is found. So you will get XR minus X, and you will get YR minus Y. The error in X direction and error in Y direction you will get. And based on the error, the controller will act on them, and it will be giving the required inputs to the mobile robot, where it will be given to the motors. Okay, motors, what you will give? The velocities. Velocity of right wheel or left wheel. Okay, so see, this is what you have to give to the robot, so that the mobile robot will move from the door location to the destination location in order to reduce this error. So that is the task of this controller. So this is how a typical mobile robot controller block diagram will look like. And if you look at a manipulator, so there that is not going to be very simple as in this case, because if you consider a manipulator, so suppose if you consider a 3 degree of freedom manipulator, okay, so for example, if you consider this as 3 degree of freedom manipulator, there's theta 1 here, theta 2 here, and theta 3 here. 3 angles are there, okay. So currently the robot is at a particular point, theta 1, theta 2, theta 3 position, and it has to reach the final destination. It will be given theta 1 final, theta 2 final, and theta 3 final. Some values will be there. So it is currently at this point, this position, and it has to reach this position. Not only this position, but also there are some velocity requirements which is denoted as q dot, and there are some acceleration requirements which are q double dot, so which are actually represented as maybe theta 1f. That is at the final point, what should be the velocity, angular velocity of joint 1, what should be angular velocity of joint 2, and what should be angular velocity of joint 3. And similarly, the accelerations, corresponding accelerations will be theta 1f double dot, theta 2f double dot, and theta 3f double dot. Okay, so it is not as simple as in the case of the mobile robot case, wherein so you need to give all these inputs, and these are actually designed by means of the trajectory planner. Okay, the trajectory planner, what it does is you give the desired task, the position and orientation of the end effector. The trajectory planner will be trying to find all these things. So what it does is, instead of this theta 1f, theta 2f, theta 3f, not only this, it may be actually, it will be like, because as it's a planner, what it does is it will be finding theta 1f of t, theta 2f of t, and theta 3f of t. Okay, so in this way you need to give the inputs, and there will be some sensor or sensory feedback which is taken in order to know what is the current position, what is the current velocity. That will be fed back and it will be compared, and this controller will try to reduce the error. Okay, so this is a typically what a model based controller for a manipulator is trying to do. See all these points clear to everyone? Any quick doubts? Because as we move on, see, these basic ideas are required. Any quick doubts? Anyone? Okay, so I hope there are no doubts. Now, see, I am going to consider, basically I am going to concentrate on differential drive robot configuration only, because it is easiest robotic configuration to start with. See, this is a typical robotic differential drive configuration. So even though it is very simple, see, this is having only 2 wheels. Now you cannot see a caster wheel. So it may have a supporting wheel at the back side in order to stabilize that. If the wheel size is too big, no, it will be stabilizing on its own. You don't need a caster wheel, but sometimes here you could see a caster wheel, which is, these two are driven wheels and this is a caster wheel. Okay, so now see, it is capable of so many, so if you wish to use it for surveillance or anything, you will be able to do that even with the simple configuration. The only thing is that you need to get a model for the system. So you should know what is the wheel radius. So wheel radius means the radius in the wheels, and what is the distance between the wheels, which is called wheel base. So you need to have an idea of all these measurements so that you can get the perfect model for the system. So what we do is, so these are the basic differential drive configurations. And see, this is a comparison of a differential drive configuration with other configurations. See, so if you look at this now, these 2 wheels are driven by motors. So a motor will be kept here as well as here, but this is for support. But if you look at this now, this is steered. Okay, so that means, So if you consider an auto rickshaw, what is happening? In order to take a turn, you are actually changing the direction. This is being steered. But in this case, no, the change in direction, left turn or right turn, is obtained by adjusting the speed of left and right wheel. But in the case of car and an auto rickshaw, the direction change is obtained by this steering wheel. In this case, no, we don't have a steering wheel. We have only a supporting wheel. Change in direction of the vehicle is achieved by changing the velocities of this one and this one. So this is a different configuration. See, this is a standard differential drive configuration, and this is a like steered vehicle, and this is another configuration which is called an omnidirectional robot. So the advantage of an omnidirectional robot is that it will be able to move in any direction without so it can move sideways also. But if you look at all these configurations, it won't be able to move sideways like this. So it has a typical turn radius constraint, so only it will be able to take a turn with that minimum radius. Okay, so it won't be able to move in any direction as we wish. Hope you got some idea about these configuration, but we will be mainly concentrating on the differential drive configuration. So this is a very simple differential drive configuration, which for getting started with MATLAB programming, this model will be fine. And then you can add on complex parameters or equations for the other robots you are working with. So if you consider this, see, as I was mentioning earlier, you don't have to use some complex equations for modeling. Just start with very simple model. Okay, so what you need to do is you assume this robot as a point object. If you assume this robot as a point object, okay, so you just assume this robot as a point object which is moving with a velocity v, linear velocity v, and an angular velocity omega. And if you consider some x-axis in this direction and y-axis in this direction, you will be able to write the equation of motion as x dot. X dot means dx by dt. That is rate of change of x in x direction, rate of change of x in this direction. dy by dt means rate of change of y in this direction. Okay, so it is v cos theta is rate of change of x. This is v sin theta, and theta dot is equal to omega, which is the angular velocity. So in order to have a feel of angular and linear velocity, just imagine that your car is taking a turn in the main road. So your car will be having not only the angular velocity, it will be having linear velocity also. But suppose if the car is cruising in the straight road, in a highway, it will be specifically mainly having the linear velocity only. It will be moving in the forward direction, right? But if it is taking slight turns and all, angular velocity also come into play. So you can just imagine your vehicle in that way and compare that with a very simple robot which is moving with angular velocity omega and linear velocity v, so that you will be able to get a very simple relation like this. Okay, so ultimately what I need is, so what I told you is that for model-based control, I need input-output relations. Input-output relations, okay? So I got a relation here. So this is x position, the rate of change of x position, rate of change of y position, rate of change of angular position, okay, or the heading, the heading angle. So if you look at this example, what do you think is going to be the input I am going to give, and what is going to be the output, which is, so the desired output. So what I may require is, see, the mobile robot is at the entrance of the room, and it has to move to the right corner of the room. Okay, so it is currently at some x0, y0, theta 0, and it has to reach some xg, yg, theta g. So, so the desired output I will be considering as xg, yg, theta g. In the first level, that is fine, okay? But maybe no, so if you are seriously doing some research or some other works, no, maybe you may have to consider not only the position, you may have to consider xg dot, yg dot, and theta g dot. Sometimes you may have to consider, okay? So for the time being, I'll be considering this. Okay, so I am at x0, so my mobile robot is at x0, y0, theta 0. Okay, which is at the location in the near the door of the room in which I am sitting, and this is the right corner of the room, and that location is this. I have to move the mobile robot from here to here. What is the input I am going to give? If you look at this relation, I can see that it is the linear velocity and angular velocity. So if you look at this particular expression, okay, it is seen that it is actually the linear and angular velocity which are the control inputs. So correspondingly, what I have identified is, see, as I told you, if you wish to make a system autonomous, the first thing is finalize which are the inputs and outputs. Okay, so we have finalized that inputs are inputs for the input for this is inputs for this particular symbol system are V and omega, and outputs I am going to consider are X, Y, and theta. Because now from X0, Y0, theta 0, I have to reach XG, YG, theta G. So that is why I have decided. See, I have decided, okay, these are going to be my control inputs, and these are going to be the desired outputs. So in this way, I got the relation. But see, I am not happy with that. Why? Because no, the mobile robot is actually driven by, see, there is a motor here. There will be one motor here, which is for corresponding to left wheel. And there is another motor here, which is attached to the right wheel. I wish to know, I wish to consider the speed of the left wheel velocity, which is omega L, and speed of right wheel velocity, which is omega R, to be the input. Because no, see, when I am using motors for controlling this robot, see, what will be the input I will be giving? See, I'll be changing the motor speed, right? So because now, suppose if I wish to move the robot in a straight line, what I will do? I will make omega L equal to omega R equal to maybe some 200 RPM. Okay. And suppose if I wish to take a turn like this, what I will do? I will reduce. Maybe I'll run this at 50 RPM. And I will run this at 100 RPM. What will happen? It will take a left turn. So suppose if I wish to take a right turn, maybe I will run. So in that scenario, I'll be increasing the speed of this 100 RPM here and 50 RPM here. See, so I am sad because, see, my control, actually I'm controlling the motor speeds, right? But see, unfortunately, when I look at this, see, even though I told you it's very simple model, see, I am having in my hand or V and omega as a control input. So you need to explore, okay, is it possible to represent these V and omega in terms of omega R and omega L? Then I am happy. Okay, so if I can express V and omega in terms of omega R and omega L, I am happy. See, everything is in my hand. It's just a matter of getting that relation, and I'll just change left wheel and right wheel velocity so that I can move my robot from the entrance of the room to the right corner of the right-hand corner of that my room. So that is possible, right? So I'm happy if I can get that relation. So you will get that relation provided you know the wheel radius and the wheelbase. So based on those values, you will be able to, if you wheelbase, I have already mentioned, it is the distance between two wheels. So I'm so happy because now what I have done is I see this relation. So if you refer to any book, you will get how you are arriving. So if you wish, just apply common sense, because the linear velocity will be proportional to sum of left wheel and right wheel and left wheel velocities, and the angular velocity will be proportional to the difference in right wheel and left wheel velocity. So I'm so happy because see, in this way, if I represent, I got the inputs as equal to, I have identified the input as right wheel and left wheel velocities and outputs as equal to x, y, theta. Done. See, this is what you have to do for any robotic system in your hand. You identify, okay, directly controllable parameters can I get hold of, so that everything is in my hand. Yes. So I'll be able to control the vehicle as I wish. Okay. So any quick doubts, anyone up to these points discussed so far? Okay. So now what I'm trying to do is, so this is how you start with. So you have the mathematical model in your hand. Now you will be able to make the system autonomous. So we are engineers. We are not going to work with trial and error method. We will be coding in such a way that we'll be implementing the algorithm in such a way that I will say at instant t, what should be each instant t, what should be the left wheel and right wheel velocity, so that my mobile robot can move from the desired start point to the desired goal point. Okay, so that's what we are going to check. So we'll start with a very simple example of moving to point. Okay, so maybe before doing this task, what I can do is I will directly move on to the simulation. Any quick questions, anyone?
Jisha ma'am. Ma'am, could you please unmute yourself?
Oh, sorry.
Okay, ma'am.
Okay, so see, we'll be modeling this equations. So we have, I told you that V and omega are the inputs and x, y, theta are the outputs. So suppose if I decide to move in a straight line, okay, so you assume a straight road and my car is moving straight like this. What should be the V value and what should be the omega value? Tell me. Some sample values are fine. I have to move like this, straight road. What should be the angular velocity of the vehicle? What should be the linear velocity of the vehicle? Come on, wake up. All are sleeping. Come on, tell me. This is a very simple question, right? Just imagine your car. The car is moving in a straight road like this. Straight movement. Yes. What should be the angular velocity? Tell me. Come on. No one is driving car. So I could see Sri Shankar. Sri Shankar, I could see you in front of a car. Are you there, Sri Shankar?
Hello.
Yes.
Yes, ma'am.
Yes. So when you are driving your car in a straight line, straight road, what should be its angular velocity? Straight road, highway.
Yeah. So it's we should follow 90 degree, right?
90 degree. No, I am asking about asking your car.
Yeah.
Is moving in a straight road, in a highway.
Yeah. Okay, ma'am.
Then what should be its angular velocity? What do you mean by angular velocity?
Ma'am, is it 0?
Yes, it is 0, right?
Yeah.
Angular velocity is 0. Okay.
Yeah.
So then what about the linear velocity? Suppose if you wish to move in a straight, move straight in that highway road.
Highway road, yeah.
What will
Moving
you do?
straight.
Huh?
Moving straight.
Yeah, moving straight means you. So what I wish you to answer is in this way. If you imagine what should be the angular velocity, the first point is correct. See, omega should be equal to 0. So
Yeah.
suppose if you give a constant v, will it move straight?
Constant B. Yes, ma'am.
Yes, it will move, right?
Yeah.
Yes, that's it. So that is, if you wish to move the vehicle forward in a straight line motion, what you need to do is you need to just give a constant beat. You can decide. So what I'm going to do is I'm going to give a combination. Linear velocity is equal to 1 and angular velocity equal to 0. And suppose if I give v as equal to a constant value, let it be 1. And if I give omega is also equal to some constant, how the vehicle will be moving? Suppose first case, what you told is correct. Because if I wish to move the vehicle forward, then straight line movement means this is 1, this is 0 will work. So suppose now you consider the case when v equal to 1 and omega equal to 1. What will happen? How the vehicle will move?
V is equal to 1.
Or some constant. You imagine your car is moving at some constant linear velocity and some other constant angular velocity. So how the car will be moving?
Curve.
Yes, it will be taking a curve like this, right? So if you drive for so much time, maybe it will take a circle also. I don't know. If it's a ground,
circular motion.
Yes, so it will be a circular motion, right? So that is what. So what you need to know is, you need to it's just a matter of imagination. Okay. See, I have decided that inputs are V and omega. That is in my hand. And I need to reach the desired destination. What should be the V and omega so that I can drive the vehicle forward, or I can drive the vehicle through a curve, or if I wish to take a circular path. So it's just a matter of identifying what should be the input, and if you give, you will be able to do that. So now what I am explaining here is, see, instantly I am not finding each instant, corresponding to each instant, I am not trying to find V and omega. What I am trying to find is, see, overall in open loop, if the vehicle is to be moved, what should be the angular and linear velocity. So this is what I am going to show you now in simulation. So, so from the feedback, what I understand is you know how to simulate. You know the basics of MATLAB. Maybe in this I'll be using this. I'll be explaining. Okay. So can you see this program?
Yes, ma'am, it's visible.
Okay, so what I am going to do, so this is a program I am going to run, so which is actually the open loop simulation, open loop simulation of kinematic model. Okay, model which is x dot equal to v cos theta, y dot equal to v sin theta, and theta dot is equal to omega. So we are starting with this open loop because I am going to give some fixed linear velocity and some fixed angular velocity and see how the vehicle is moving. Okay, I'm not using a controller, not using any controller. Okay, so look at this. So this is how we have to start. So what I have taken is, I'll be starting at time t equal to t0 equal to 0 start time and tf is equal to 10. So up to 10 second, I will be simulating 0 to 10 seconds. So now what I need to do is, see, this is a robot. I need to say what is the initial position of the robot. See, here it is seen that x0 is equal to 0, 0, pi by 3. So that means initially the robot is at x0 is equal to 0, y0 is equal to 0, and theta 0 is equal to pi by 3. So this is the initial position. I need to mention the initial position here. Now, so you can change whatever you want, no? You can change. Now what we do is, we need to simulate these equations. So for simulating these equations, so if you look at these equations, these are all first order ordinary differential equations. So these first order ordinary differential equations can be simulated using MATLAB with this function ODE45 or any ODE23, whichever ODE is required you can take. But sometimes some equations are very hard to integrate. So depending on the type of equation you have, you need to choose the corresponding ODE format. So I have taken ODE45. So now what I need to do is, this is the main command, and I need to write all these things in a function. The model of the robot is written in a separate function. If you look at that, the model is entered in a different function. So this is just a main program. Okay, so this is a main program, and the template or the format for ODE is that ODE45. In bracket, you need to mention the function name, then what is the time interval, and what is the initial position. So what it does is, from the initial position, it is integrated forward for 10 seconds. So as you wish, you will be able to do that. So when you integrate, you will be getting, see, you give V value, you give omega a value and integrate. So you will get next point, what is x, y, theta. Again, you give V and omega at next point, what is x, y, theta. You will be getting all these values in a vector form, and that answer will be stored in this x ans. Okay, so x ans is actually, so I have, see, any variable you can give, whatever. I have taken x ans. So it will be actually, it is the vector of x, y, theta from t0 to tf in the vector format like this. So this will be x0, y0, theta 0. Next will be x1, y1, theta 1. Like that, finally, xf, yf, theta f. So you will be getting a 3-column vector here, because in this case, we have 3 states. 1, 2, 3, 1, 2, 3, 3 states. And now everything done. So you got all these things, you got the answer. It's just a matter of plotting. So what I wish to plot is x versus y. In xy plane, how the robot moves. So that's what I wish to see. So I have taken x ans of all comma 1. So that means it will be taking this column all comma 1, and all comma 2 means it is this column. So it's just a plot of x comma. So you will get a plot of x comma x versus, see y versus x plot you will get. So that's what I wish. I have got this, and I'll be just giving labels, x label, y label, and title also I have given. Okay, so that's all about the main program. In the function, see, this equation is to be entered. So this equation is entered like this. See, what you need to do is, because we have to finalize. See, what is the size of x? Because there are 3 states. From this, I will be knowing how many states are coming. It is actually coming from here. Just coming from here. Okay. So that is how you get. So size of x means, in this case, it is 3. So initially, dx will be initialized as equal to 0, 0, 0 to get started. Then dx of 1 means x, dx of 2 is y, dx of 3 is theta. So instead of x, it is dx of 1. Instead of y, it is dx of 2. Instead of theta, it is dx of 3. So we will write the equation as v cos theta. So see, if you look at this expression, x dot is equal to v cos theta. So how do you get, see, if you mark x is equal to x1, y is equal to x2, and theta is equal to x3, the equations are changed as x1 dot is equal to v cos x3, x2 dot is equal to v sin x3, and x3 dot is equal to omega. This is the equation when you represent the same using x1, x2, and x3. So that is what is entered here. It's just a matter of entering that. So suppose even though you are having 24 states for the system, it's just a matter of adding all those things, dx of 4, dx of 5, you can simply add and simulate that. So hope this point is clear. So I'll just show you this program also. See, this is the open loop main program, and this is the function. And what I'm trying to do now is I'm going to simulate this open loop model with v equal to 1 and omega equal to 0, which means that it will be moving in a straight line. So what I'll do is this open loop I will be simulating. I'll run this. See, it is moving in a straight line. When I have given v is equal to 1 and omega equal to 0, it is moving in a straight line. in open loop. So see, so before real hardware implementation, these kinds of testings will work, because now, okay, if I give this input, these input combinations, what will be the XY position also? The robot is actually moving in a straight line like this. Now, suppose if I wish to move this robot, this is actually open loop only. A closed loop means at each instant, the control inputs is to be calculated. So instead of v equal to 1 and omega equal to 0, if I give v equal to 1 and omega equal to 1, then I save that and then I run this once again. See, it is moving in a circle. So it's just a matter of intelligently identifying what should be the control input to be given. So the control input in this case are linear velocity and angular velocity, even though practically it is not possible. Practically it should be the angular velocity and left wheel and the right wheel velocities. Okay. Any doubts? Because now only if you understand this, you will be able to understand the upcoming examples. Any doubts, anyone? Because no, this is a very simple program. So we'll be building upon this program. We'll be adding extra lines to this program to make it closed loop. Or suppose if you wish to make the same, implement in a hardware, how can we do that? So all those things will be discussed now. So before that, if there are any doubts, I can clear.
Participants can unmute yourself and ask questions.
Okay. Okay. So, so now we will move on to another simulation. See, so you may be thinking how I can implement the same in hardware. So in hardware implementation, what I need to do is, see, even though I say that, see, b equal to 1 and omega equal to 0, maybe this I will take so that it is more clear. See, in the previous example, now you may be thinking, how can we give v and omega values directly? So actually what we can give is what the left wheel and right wheel velocities, right? So if I simply change the program in such a way that if I have an expression for omega and omega L, I have already told you, right? And if you need to know what is the wheel radius and wheel base, so you know what is the relation between the linear and angular velocities of the vehicle and the linear, the right wheel and left wheel velocity. So if you know this expression, done. I know what is the right wheel velocity. I know the left wheel velocity. So if I know this, so it's just a matter of finding this. Now, see, at each instant, what is omega r? Okay. What is omega L? I am getting from these equations. So it's just a matter of coding. You just see this in hardware so that at each instant you drive the vehicle at respective speeds. See, there is no need of trial and error. Just write this thing. So the program will work and you will be able to move the robot to the beside. So this one is actually I have opened up that v and omega expressions in order to express in terms of right wheel and left wheel velocities. So hope this open loop simulation. So this also you will get similar result. See, moving to point and suppose if you make this one and run it again, it will be moving in a closed loop. Sorry, not closed loop, in a circular format. Now we will see how to do closed loop examples. So closed loop examples, very common example, a very simple example is moving to point. Okay. So moving to point means, see, currently I am at one particular position. Just imagine the robot is just kept near your seat. See, you are sitting in a particular room, right? So, so suppose your chair and table are here. This is your chair and table, and this is the robot position R0. Just imagine the robot is at this particular position X0, Y0. If it will be having theta 0 also. But to get started, we'll start with this. And suppose it is near you, and you need, the robot has to reach the destination XG, YG. Okay. How can it reach here? Using closed loop control. Trial and not by trial and error. Directly, each and every instant of time, we will be able to compute what is the left and right wheel velocity. So for that, no, you don't have to go for very complex expressions. You need to, what you have to do is, you just give a linear velocity to the vehicle, which is proportional to the total error. So error means there is some exposition error. Exposition error means current X position and the goal position, and current Y position and goal position. So this is actually the X error in X, error in Y, and this is the total error. So you give a linear velocity which is proportional to the total error, and you give an angular velocity in such a way that see, suppose, see, if you consider the scenario like this, see, suppose this is XG, YG. Okay. And this is theta. Okay. So the robot should be moving towards this angle, right? So we call this as theta star, the desired theta star, which is actually, how do you get Y difference divided by X difference? What is Y difference? It is YG minus Y divided by XG minus X. So when you find tan inverse of that, you will be getting this theta star. So whatever be the initial position of the robot, it should align like this and move towards this goal. So if you make the robot move in such a way that the angular velocity is proportional to this angular error, which is the current theta of the robot and the desired theta star of the robot, what happens is the robot with this V and with this omega, the robot will be able to move to the destination. So if you look at this block diagram, this explains how this can be implemented. So this is basically the robot which we are considering. Wherein we say that linear velocity and angular velocity are the inputs to the robot, and X, Y, and theta are the outputs from the robot. So we got V as equal, linear velocity as equal to, see, kV into, we are trying to implement a proportional controller, very simple controller to implement. So it's a proportional controller. So what we do is some gain into position error. So that's what we are trying to find here. See, XG means it's actually XG, YG. And from here, see, if you look at this, X and Y are coming here, X and Y. So here you will be getting X, Y. So at each instance, the robot is moving forward means X and Y will be changing. So each instant at this point, see, 2, 2 is shown. So that means it's two signals are coming in. So at each point outside this this point, you will be getting XG minus X and YG minus Y. You will be getting. So you are getting actually X error and Y error. So U1 will be X error square. This is Y error square. Okay. So square root of X error square plus Y error square is coming, and this is the gain, and that is given to, so that is this expression. So from this expression, we will get that. Okay. So this is what is fed as the linear velocity. And the angular velocity is taken as a difference of theta star and theta. So for that, what we have to know is, you should know what is the actual theta. See, theta is coming from here. Okay, theta is coming from here, and this is theta star. A tan 2 means it is tan inverse of yg minus y divided by xg minus or whatever, y minus yg, whatever it is. So theta star is coming here, theta is coming here, and see, whenever you are doing robotic problems with orientation into consideration, you need to make sure that always the angle lies between minus pi and plus pi. So I have already, so this function is also used wherever. So you need to make sure whenever you are doing robotic simulations, considering this orientation and angles, you need to make sure that always the angle lies between minus pi and pi. So this function helps to do that. And now there's a constant gain, which is, so it's just a matter of implementing this. So the block diagram shows like that. And you need to just multiply that by the corresponding gain, and that is to be given to the omega, so that you will be able to reach the destination with this simple proportional controller. You will be able to reach the destination. So now I'll show you how to simulate the same. So I have written a program, moving to point. So it's the same as the previous one. The main function is same, but the only thing is that in this part I have changed. This part I have changed. I will show you here. That will be easier. See here, in the function part only I have changed. Okay. So what I have to do is in open loop case, what we did in open loop directly I have given what is V and omega. But in closed loop, no. For the desired task to be accomplished, what should be V and omega, automatically the controller will compute. So that's what is happening. So if you look at this now, what I've given is there are two proportional gains, kV and k theta, and the destination is to be given. And see, the linear velocity is found as equal to kV into square root of x error plus y error. And then I need to find what is theta star, tan inverse of yg minus y, comma xg minus x, and then theta error is to be found, that is, which is actually theta star minus theta. So that is found by this equation. So as I was mentioning, it's not just theta star minus theta, it is angle diff, to make sure that the angle, make sure that the angle lies between minus pi and pi. And now, so we got V and omega also, you will be getting. So done. See, you don't have to do any trial and error. You got the actual linear and angular velocities. At each instant, you will be getting these values. So, and suppose if you wish to drive the robot, you know what is the relation between, you know how to represent V and omega in terms of omega R and omega L. So try to find what is omega R, try to find omega L, and you run the two motors. Okay, two motors with these speeds, automatically the robot will be reaching the destination. Okay, so this is how you need to do this task. See, moving to point, I'll show you. See, 5, 5 is the destination point I have chosen, and the robot is starting at 0, 0, pi by 3. Okay, so, okay, see, 0, 0, pi by 3, the robot is reaching there. It is reaching 5, 5. You can see that, right? So now I will change the, maybe I'll put hold on and, so I'm taking a different position, and I'll take a different color and try to run that again. See, from 1, 0 also it is reaching the destination. Okay, so now if I change the position from 0, 1, maybe a different color. See? So wherever I am starting, it is reaching 5, 5. Okay. So in this way, you can check at any point, if you simulate, the robot will be able to reach the destination using this controller. So you don't have to try it with trial and error. See, automatically the robot is reaching the destination 5, 5. Any doubts, anyone? No? See, this shows simulation from different points. So see, from different initial positions, the robot is able to reach the position 5, 5. Okay, so you will be able to simulate this. It's just a matter of changing. So if you look at this now, the orientations like this. So here the orientations change. You can change position as well as orientation. You can get the simulation. And next is following a line. Okay, so all of you might have seen your students building line follower robots, wherein the line will be physically seen, right? So a line will be marked on the floor and the robot will be moving over that. So now you consider a different scenario. So a different scenario wherein just imagine you are sitting in a chair, right? In a particular room. Just imagine a line, a straight line connecting the two corners or maybe just parallel to your table. 1 meter ahead of your table, just imagine a straight line. You don't have to mark anything on the floor, but automatically, if you know how to represent the equation of that line in that plane, you can make the robot follow that particular line in closed loop without trial and error. Okay. No need of marking the line on the floor. Okay, wherever you wish, you will be able to move the robot. So it's just a matter of representing that particular line as ax plus by equal to c, because no, you know line, the expression, the equation for line is y equal to mx plus c. So the same can be represented in this way, right? So in this case, we need actually 2 controllers to adjust steering. One controller steers the robot to minimize the robot's normal distance from the line. So that means what it does is, okay, I don't have an example. I'll be trying that. See, what it does is, see, suppose this is the imaginary line I am assuming, and suppose the robot is at this particular position. Robot initially is at this position. So this requires 2 controllers to adjust steering. One controller steers the robot to minimize this distance. This is the normal distance between the robot at any point of time. This distance is computed and that is to be minimized. So that is found by using this expression. Okay, the dot product is taken. So actually what you need to do is, see, suppose you have a line like this where A, B, C are real constants and A and B are not both 0. The distance from the point, this point to this line is given by, it is just a matter of, see, x0, y0 is the robot position. And these are the coordinates. You need to just find absolute value of ax0 plus by0 plus c divided by square root of a square plus b square will give you the perpendicular distance between this point and the line. So once you get the line, you need to try to minimize this distance, right? So you need to give a value velocity which is proportional to this, which is trying to minimize this. So you may have to give a negative sign. So that is what, see, the proportional controller, we will give minus kd into d, where d is actually the perpendicular distance between this robot and the line which the desired line which you wish to follow. So this will turn the robot towards the line. So this is what we do is, this is one of the terms corresponding to the angular velocity. So this is the first term. And the second term, what we do is, it will adjust the heading angle. The first controller, it is trying to adjust the distance, and the second controller tries to adjust this heading angle. So for finding the heading angle, C is, so it is just a matter of writing as y equal to mx plus c. Okay, so in this we know that slope is m. So similarly in this case, no, our equation is ax plus by plus c equal to 0. Ax plus by plus c equal to 0. So if you adjust this in such a way that it is written as y equal to mx plus c form, you will get m as equal to this. So that is what is written, which gives the desired, which is a slope of the line, which is minus a by b. So that is a desired angle which we need. And what we do is we will find the difference. It is actually theta star minus theta. But as we are using angle diff, because no, to make sure that the angle lies between minus pi and pi, this difference is shown. That's it. And we'll be multiplying that by a proportional gain. And what we do is we will drive the robot with an angular velocity which will try to reduce the perpendicular distance between the robot and the line, and also it will try to align towards this desired heading angle. So this will turn the steering wheel so as to drive the robot toward the line, and it will try to move along the particular line. So it is not a trial and error method, right? Each and every instant you are having a particular value for omega from this expression, and we know the angular velocity you can give a constant value, and you need to compute at each and every instant this value, and that is to be fed to the robot, and the robot will easily follow the line, desired line. So this is the following a line example block diagram, wherein the only difference is that v is directly given, that v is taken as constant, and angular velocity is found as sum of these two terms. It is minus kd into d plus kh into theta star minus theta. So that is actually computed by using these two functions, and it is fed to this term omega, angular velocity. Okay, so now see, if you simulate that, you will be getting this result. I'll just show you the example. So following a line example is also there. See, here also the only difference is that in the main program I have just plotted the line also, because ax plus by plus c equal to 0 is the line. I have taken a equal to 1, b equal to minus 2, and c equal to 4. And I have plotted how to plotted the reference line. And here now in the code, what I have done is, see, just it's similar to the previous one itself. See, it's instead of a, yes. Any doubts?
No, ma'am, you can continue.
So see, all those expressions are given here. So instead of A, B, C, see inside this program, I've taken as L1, L2, L3, and the corresponding expressions are written, the same expression which I have shown. An angle diff is also calculated. And then when I run this program, you can see that, see, so this is a reference line. The blue line is the reference line, and this is the start point, and the road is able to follow the line like this. See, there's no need to physically mark this line on the floor or so. It's just a matter of imagining the line and finding the expression for that line, so that at each instant you will be able to compute the left wheel and right wheel velocities of the robot, and you can drive the robot in order to follow this line. Any doubts? Okay. So then we move forward for following a path example. So see, if you can simulate, or if you can try moving a robot in a straight line and a curved path, no, any path you take. So for a car also, it's going to be a combination of straight line and circular segments. So here what I'm going to show is how can we make a robot follow a path. Okay. So in this case, the only difference with the previous example is that the moving to goal point is that, see, the same block diagram we can use. The only difference is that, see, in the first case, we have given xg as equal to 5 and yg as equal to 5. So instead of that, you need to give the reference path in this case. Other components in the block diagram are the same. So the first question in our mind should be, suppose if I have to move the robot through a circular path. So that's what I'm going to do. If I have to move the robot through a circular path, so just imagine that your car is to be moved in a circular path like this. Then what should be the x reference to be given and what should be the y reference to be given? Okay, so the easiest one to start with will be, let me erase this. The easiest one to start with will be, just imagine that this is the origin and you have to follow a circle like this. So can you just imagine your car moving in a circle like this, and this is 0, 0, the origin. Okay, so what should be the x reference and y reference? So if you look closely, you can understand that if you give sine t and cos t as x ref and y ref. So suppose if you try to plot the x profile versus y profile, if the car is moving in a circular path like this, and suppose if you wish to plot xt versus t, then it will be a sinusoidal curve, and yt versus t will be a cosine curve. Okay, so then you will be able to get a circle. So it is just a matter, see, all these things you need to decide or finalize before executing those examples. Okay, see, the vehicle has to move through this path. So what should be the equation for that path? I need to find out. So suppose if I wish to change the center of the circle to 1, 1. So what I'll do is I'll give the reference as 1 plus sine t and 1 plus cos t. If I wish to change the radius of the circle with the same center, suppose 2, I wish to have radius 2, I can give 1 plus 2 into sine t and 1 plus 2 into cos t. So automatically you will be able to get those paths. You can see that all those paths are being tracked. Okay, so the only difference between the moving to point problem and following a path is that you need to just give the path there. I'll just show you in the program. Let me check. Okay, first of all, I'll take a sine t cos t example wherein you will be getting, so this is actually a closed loop example. See, because I have put hold on, I think. See, so this was the initial position of the robot I have taken. So initial position is 0, 0, 0. The robot is initially at 0, 0, 0, and I have given a circle expression with 0, 0 as the origin. So if you look at this, you can see origin, center of the circle is 0, 0, and the radius is how much? It is, radius is 1, 1. See, it is lying between, I think it is how much is the radius? It's not clear. So it's sin t cos t itself. Let me run once again. Okay. So if you look at this, the respective radius, see if there is tracking error, you need to adjust the proportional gain so that the error is minimized. So here, if you look at this, no, the radius is 1 because no, this radius, this is radius, this is a diameter. Diameter will be 2, and the center is at 0, 0. Okay. Now, suppose if I wish to change the center to 1, 1, I can just change this expression here and save it here and run that, so that, see, at the different point 1, 1, I'll be getting the same circle with the same radius. And if I wish to change the radius, I can just change it here. So suppose if I give a bigger radius, that also I can give. See, but there seems to be some tracking error, not exactly 6, you could see, slightly lesser, right? So only if you draw the reference trajectory, you will see. So what you need to do is, so those kind of tuning I have not done. See, what I have taken is, see, I have taken just kV equal to 1 and k theta equal to 1. So you can just tune these parameters so that the tracking error is minimized. Okay, so in this way, we'll be able to work with all those examples. So see, all these are very simple examples to get started mobile robotics programming with MATLAB. Okay, so now I will just show you some, any quick doubts to anyone? So, so now what I'll show you is that, see, these are very simple examples so that you can start programming with MATLAB. Very simple robot. So now what you can do is, so there are, MATLAB has provided so many examples corresponding to robotic system toolbox. Okay. So if you go to that link, no, you can see all those examples. So you can explore all those possibilities. So I have taken that link. See, this is the, so if you click that link, no, it will be reaching here, robotic system toolbox. You can see, getting started with robotic system toolbox, manipulator algorithm, mobile robot design, mobile robot algorithm design, mobile robot modeling and simulation, coordinate transformations and trajectories. So all these are readily available. So different algorithms are given there. See, and this is exclusively for mobile robots, different, see, mapping, laser scans, localization, different functions are readily available. See, all these programs you can test. It's readily available, given by MATLAB. And this is a very simple example of path following for a differential drive robot. So they have given program for that also. And it is self-explanatory. See how to get started, and see all these steps are directly given here. See, I have taken that code here itself, and I'll just show you. See, this is that program using waypoints. I'll just run that. See, you can simulate this. The robot is moving through different waypoints which were priorly set, and the robot will be moving through those waypoints easily. So all those details are readily available from the links at which I have given. So maybe those who wish to continue working with this can refer to those sites and start working on that. And there are other examples too. See, pure pursuit controller, and there are different kinematic models are also simulated. So all those things you can refer to the links given. So I'm about to conclude. So So generally robots are dynamic systems represented as linear or non-linear models, but exactly speaking, they are non-linear models. So based on the requirements, you need to choose the kinematic or dynamic model. But the thing is that you can just start with very simple model, and you need to just identify which are the control variables, state variables out. So you need to just find out the input output variables from those equations. And depending on the model, suitable controllers can be designed, and before implementing the same in hardware, all those things can be tested in simulation platforms like MATLAB, so that confidently you can proceed with the design and implementation of controllers or these algorithms in MATLAB. Okay, so with that I conclude. Thank you all for your patient listening. If there are any doubts, I'm ready to.
Thank you so much, ma'am. We would be now presenting the queries on screen. Ma'am, are you able to see our screen?
Yes. How to transfer this MATLAB model to hardware controller? See, model is to be a model. See, if you consider x dot equal to v cos theta, y dot equal to v sin theta, theta dot equal to omega, we are using instead of the real robot. In the robot, what we need to give is in hardware part. What you need to do is you will be using some Raspberry Pi or Arduino board controller, right? So suppose if you are using if you are trying to use the moving to point controller, how will you execute that? Okay, so you have a mobile robot. Just imagine two motors are there. Okay, for driving right and left wheels, and there is a controller, and there should be a sensor, which is a sensor which gives you an idea of what is its current x, y, and theta. So we need to have some wheel encoders in order to know what should be the x, y, and theta position. And suppose if it's the robot is moving fast, even if you can use orientation sensors in order to get the orientation also. If it is moving slowly, we can rely on wheel encoders in order to get the values. So what happens? See, t equal to 0. At t equals 0, you know the position of the robot, which you will get from the wheel encoder readings. So x0, y0, theta 0 readings I will get from. So first line will be that. Next point, what it does, it has to, see, you will give xg equal to 5 and yg equal to 5 in the code itself. So next line, it will find what is xg minus x, because your encoder has given what is the x value. Next line, it is yg minus y. So you got x error, y error. So now next step is v is equal to kv into what square root of x error square plus y error square. So you got the value of linear velocity. Similarly, you have an expression for angular velocity. So from that, you find what omega r is equal to what and omega r L equal to what. You got the value. Now you got omega r equal to 500, maybe 100 RPM. So what you do is you run the motor. You will be for a particular microcontroller you are using. There will be a command for running the motor at 50 RPM, right? So you got omega r equal to 50. So drive the motor at 50 RPM. Next is drive the right motor at the RPM you are getting. So in that way, you need to just write that code depending on the controller you are having. So in addition to that, see, there is something called, I think from MATLAB also you will be able to embed code. So I have not done that in hardware. So the same, all those details, you will be able to get from here, wherein see in the robot, see how to generate code for code generation, and robotic system toolbox supported hardwares are also available. So all those details you can get from here. So what I was telling is, whatever is the controller you are using, whether it is Raspberry Pi or Arduino or any controller, you will be able to execute that in this way. And next is, can you suggest one good reference for mobile robotics with MATLAB? Peter Cork. The book by Peter Cork, you can search. That is a very good book. And can we model swarm robotics using MATLAB only? Yes, you can. The only thing is that in swarm robotics, each and every robot is not individually modeled as individually modeled as some equation. So they'll be modeled as point objects. Even with MATLAB, you will be able to do that. There is no problem. Hope I have I have answered the question. So I don't know whether those who have asked the questions are happy with the answer, or some more details they require. If they need, they can ask.
Thank you, ma'am. Participants, do we have any more questions? Ma'am, I think we can wind up the session.
Okay.
Thank you so much, Jisha ma'am, for the highly inspiring time with us. Your remarkable depth of understanding of the subject has made the session an exceptionally informative one. I'm sure the participants would have certainly benefited from your breadth of knowledge and depth of expertise. On behalf of the Department of Electronics at TIST, I once again express my gratitude for your presence that has definitely enriched the session, ma'am. Thank you so much.
Thank you all, and have a nice day.
Thank you all participants. We are winding up the session for today. We'll begin the session tomorrow at sharp 9:30 a.m. Thank you all and have a great evening. Participants, the exam would be conducted in online mode on the last day of the STTP. We will be informing you the same through WhatsApp group.